Okay. Okay, welcome back to the last session of the flat bands mini-colloquia. So basically, today we'll start with our invited speaker, who is Yuya Shimazaki from the group of Akashima Mobile at ETH Zurich. And he will speak about correlated electrons in optically probed Moire superlattices. So Yuya, please.
Thank you for the introduction. And initially, I'd like to thank to the organizers for giving me opportunity to have an invited talk in this conference. And today I'd like to talk about correlated electrons in the Moire superlattice probe with optical spectroscopy. Initially, I'd like to thank to my collaborators, and especially Professor Atachi Mamoglu, who hosted me to do this research and supervise the project. And also, I'd like to thank to Dr. Ido Schwarz, who performed the experiment together with me. And Clemens Kurenkapp provided theoretical calculations. I'd like to also thank to Tomas and Martin for helping discussions and experiments. And of course, I'd like to thank to Dr. Watanabe Taniguchi for providing high quality boron nitride crystals. And for theory discussion, we had a collaboration with Professor Michael Knapp and Richard Schmidt from Munich and Max Planck Institute. And also we had discussion with Professor Liang Fu and Dr. Yan Chang from MIT. And I'd like to thank to all the lab members in quantum photonics group in ETH Zurich. So as it has been discussed a lot in this conference, 2D materials and van der Waals heterostructure is still a hot topic for these decades. And there are many materials, and one of the few of the most well-known materials are graphene, which is a metric system, and transition metal dicogonite, which is a semiconductor, and hexagonal boron nitride, which is an insulator. We can assemble these 2D materials together, and we can fabricate arbitral heterostructure, which is called a van der Waals heterostructure. And in addition to this stacking degree of freedom, we also have a angle degree of freedom, twist angle degree of freedom between different 2D materials. And having the twist angle, we can create a Moire superlattice as shown here, which shows a long-range periodicity and creates an artificial superlattice in the system. This Moire superlattice has been intensively studied, especially since after the discovery of the Mott transition and superconductivity by an MIT group, as everybody knows. So this has been reported in a magic angle twisted by a graphene, where the twist angle is about 1.1 degree. In this system, there is a flat band where the kinetic energy is almost quenched out. Then the electron interaction energy scale dominates the physics. And then there, high TC cuplates like phase diagram has been reported in gate tunable device. So Mott insulating phase together with superconducting domes. And also very recently, ferromagnetism and quantum anomalous effect has been reported by a few groups, including Professor Efetov in ICFO. And these amazing results has been shown by electrical transport experiment. On the other hand, in this kind of van der Waals bilayer system, and Exciton physics also has been intensively studied. And in TMD bilayer system, Moire excitons reported in 2019 by also several groups. This is the picture from one of the paper. And in this Moire lattice, excitons are trapped on each sites like this way, and then these energy levels are quantized. And also the inter-layer exciton has been studied a lot. And this inter-layer exciton is the exciton which has electron and hole in the separated layer, which has a dipole moment perpendicular. And last year, the BEC phase has been reported by the Cornell group. and in this interlayer Exciton. And then there, this Exciton physics has been studied by the optical spectroscopy experiments. So the motivation of today's talk is whether we can assess this correlated electron physics by optical spectroscopy experiment. And to do this optical spectroscopy experiment, the TMD bilayer system is a nice system because the excitons are optically accessible by visible light and to the near infrared light. And indeed, several groups, including our group, very recently reported the correlated electrons in bilayer TMD Moire lattice. And one of the system is tungsten selenide and tungsten sulfide bilayer system. And then there, the lattice constant of these two TMDs are different. And then this naturally forms the Moire lattice even without twist angle. And then this reported by the Cornell group and you see a Buckley group. From our group, we reported a molybdenum diselenide bilayers separated by a monolayer hexagonal boron nitride barrier. And from the Columbia group, they report a twisted bilayer tungsten selenide system. And then they also show the onset of superconductivity in this system. And from now, I would like to focus on this molybdenum diselenide bilayer system. So the system we studied is composed of the molybdenum diselenide, which is a semiconductor, and two layers of them separated by a monolayer boron nitride tunnel barrier. So due to the existence of this monolayer boron nitride, the Moire potential we think is rather weak compared to directly contacting TMD bilayers. And also there has been discussion of the lattice reconstruction of this Moire system when we contact the system, the layers together directly. And having this monolayer BN barrier, we think help to avoid this lattice reconstruction effect also. And this boron nitride tunnel barrier works as a tunnel barrier for the whole side, but for the electron side, this tunnel coupling is too strong to see. And the conduction band then behaves independently in this system for, due to the existence of boron nitride barrier. And by controlling the gate voltages, we can also tune the layer degree of freedom in this system. So this system has a more degree of freedom to play with compared to, for example, tungsten selenide, tungsten sulfide bilayers. So here we show I show the schematic image of the experimental setup and device. So the device. So this Moire selenide, boron nitride, Moire selenide heterostructure is encapsulated by the boron nitride insulators. And then this has a few layer graphene top and bottom gates. And we have a top gate voltage and the bottom gate voltage biases to the each gates. And this is the optical microscope image of the actual device. By using a pair of gates, we can control the chemical potential and the band alignment or electric field independently in this system. For example, if you apply positive bias on top gate and negative bias on the bottom gate, we can have the conduction band of top layer lower than the bottom layer. And for example, we can only dope the top layer. Here, I will show the basic optical characteristic of the entire device. So this is the spatial mapping of the photoluminescence signal. The area enclosed by the blue dot line is the monolayer molybdenum diselenide area, which shows the photoluminescence. And if we see this area, which we have directly contacting molybdenum diselenide bilayer, we don't see the photoluminescence. And this is well known that in this bilayer molybdenum diselenide, there's a strong interlayer hybridization at the gamma point. And then this system shows an indirect gap at the K point conduction band and the gamma point valence band. So the photoluminescence gets quenched due to this indirect gap. However, if we see this enclosed area by yellow dotted line, which is the molybdenum dicyanide bilayer separated by monolayer BN barrier, we see quite a bit of bright photoluminescence. And we think that this interlayer hybridization at the gamma point gets reduced by inserting a monolayer boron nitride barrier. And possibly this is becoming a direct gap system. At least we can say that the extonic transition at the K point is now the lowest energy optical transition in this charge neutral regime. So and here on this set, we show the actual photoluminescence spectrum. So this blue line is for the monolayer molybdenum dicyanide, and we see exton photoluminescence. And if we see the this molybdenum dicyanide bilayer separated by boron nitride barrier, we see two distinct photoluminescence signal, which we attribute to the top layer exton luminescence and the bottom layer exton luminescence. And the origin of the energy splitting of these two lines, we attribute to the strain induced splitting. And indeed, if we go across over the sample, the energy splitting of these two lines changing and even flips. So top layer exton can go to the higher energy of the bottom layer exton dependent on the position to position. And initially, I'd like to show the optical characterization of the system in the neutral, charge neutral regime. And so here we control the two gate voltages to change the band alignment or the electric field of the system. This shows the photoluminescence spectrum of this bilayer system. And indeed, we see again the top layer exton and bottom layer exton luminescences here and here. In addition to these exton luminescences, we see the interlayer exton luminescences here and here. This shows Stark shift due to the perpendicular dipole moment. So this interaction has a hole on the bottom layer and the electron on the top layer, and shows this way of the energy shift. And now this interaction here has a hole on the top layer and the electron on the bottom layer, and shows the opposite behavior of the Stark shift. So usually these interlayer extons has a small oscillator strengths. In another word, coupling to the photon or light is quite small. This is because of the electron, the holes are spatially separated, and the wave function overlap is relatively small. So in this kind of case, it is difficult to see this interaction by the reflectance spectroscopy. However, interestingly, we see the interlayer exton signal in the reflectance spectroscopy here and here. And if we magnify the data here, we can nicely see the avoiding crossing structure of the interlayer exton with the intra-layer top exton here. This tells that there is a strong hybridization between this intra-layer top exton and the interlayer exton, which has a hole on the bottom layer. So this means that these holes in this bottom layer and the top layer hybridizes through the boron nitride barrier. And this is reasonable because the valence band edge of the boron nitride is relatively close to the valence band edge of the molybdenum dicyanide. And in addition to these hybridizations, we also see the multiple interlayer exton lines, 1, 2, 3, for example, here. We think this is due to the Moire potential in the system. And the gaining of the oscillator strength is due to now the hybridization of this interaction with the interlayer exton. So the part of the interlayer exton oscillator strength going to the interlayer exton, and we can nicely see this signal in this reflectance spectroscopy. So if we now go to the opposite polarity of the electric field, which is this side, we can hybridize the interexton, which has a hole on the top layer with the exton in the bottom layer. And indeed, we see the avoided crossing between this inter-exciton with the bottom layer, intra-layer exciton. And again, this hybridization is consistent with this whole tunneling picture. And on the other hand, we don't see the hybridization of this inter-exciton with the top layer exciton. And to have this, actually, we need a coherent electron tunneling through the boron nitride. And since the conduction band edge of boron nitride is quite high compared to the conduction band edge of the molybdenum diselenide, this tunnel coupling is quite weak. And then these two layers behaves independently in the conduction band. And so next, I'd like to introduce the optical charge sensing technique we used in this study. And so to make the discussion easier, I'd like to start from the optical spectrum of the monolayer molybdenum diselenide when we introduce a charge into the system. So this is the reflectance spectrum at so gate dependence of the reflectance spectrum. So here is a neutral regime. So here is the electron dope regime, and here is a hole doped regime. And in neutral regime, we see this exciton resonance. And if we dope electrons, we see the this blue shift of the exciton energy. And then we see the additional resonance here. These two we attribute to the an exciton which repulsively interact with Fermi C carriers here, which we call as repulsive polaron. And this one we interpret as the exciton attractively interact with the Fermi C. So, for example, the energy splitting of here to here is about 25 milli-electron volt, which is a trion binding energy. And for this polaron picture, please refer this paper. And the important thing here is the blue shift of this exciton to the repulsive polaron line when we doping the system. So this is same for both electron side and the hole side. And this energy shift is rather linearly dependent on the gate voltage. And then we can use this shift of the exciton energy to detect the charging configuration of the system. So the easy way to detect the charge configuration is to plot this reflectance signal at the fixed energy here. This is the exciton resonance energy at neutral regime. So if we plot this reflectance signal, it looks like this way. So in the whole side to the neutral regime to the electron dope regime, we see the change of the reflectance signal. And we can detect the charge configuration change in the system. So this is for the case of one-dimensional gauge scan. And if we do this for the two-dimensional gauge scan, we have both top gate and back gate. Then we can nicely see that here's a neutral regime of the system, and here's the electron dope regime, and here's a hole doped regime. So now let's see the reflectance spectrum of the bilayer system when we dope the system with electron or holes. So these are the different set of the gate scans, and the spectrum looks quite complicated. But fortunately, due to the strain-induced splitting of the top layer and bottom layer excitons, we can independently access these excitons. So the top layer excitons are about 1.632 electron volt, and the bottom layer excitons are about 1.640 electron volt. So if we plot the reflectance reflectance signal at these fixed energies, we can probe the charge configuration of the top layer. So top exciton probes the top layer charge configuration, and the bottom layer exciton probes the bottom layer charge configurations. So now I show the reflectance signal magnitude and at this top layer exciton resonance and the bottom layer exciton resonance here. So we can nicely again see the change of the doping. So here we have the neutral regime of the top layer, and here's an electron dope regime and the hole dope regime. And also for the bottom layer, we see this is the neutral regime, and this is the electron dope regime, and this is the hole dope regime. By subtracting these two signals each other, we can plot the full set of the phase diagram in the system. So this is the regime where both layers are in neutral. And this is the regime where we have electrons in the bottom layer. This is the regime we have electrons in both layers. So, and this is a purely optical spectroscopy, but as people do in transport studies, we can now detect the charge configuration of the system as a function of the gate voltages like this way. And so the interesting thing happens when we go to the low electron density regime. So if we go to the low electron density regime, the electron-electron interaction energy scale dominates over the kinetic energy scale. And as it has been discussed, like twisted barrier graphene also. And then here, if we see around this merging point of 4 different regions of the neutral regime of 2 layers, and here is the electron doped regime of the bottom and electron doped regime of the top layer. Both layers are electron doped. We start to see some interesting features here. And to visualize the structure better, we take a fine gauge scan around here. And here I plot the Exciton resonance energy shift of the top layer. So so this vertical axis is the doping axis or chemical potential axis. And by doping the system, we see the energy shift of this top layer Exciton, and this energy increases or blue shifts. And then this lateral axis is the electric field axis or the band alignment axis, where we control the, we transfer the charge from the top layer to the bottom layer. And we clearly see the periodic structure in this diagram. And to visualize the data better, I took the differentiation along this vertical chemical potential axis. So now this relatively linear dependence of the increase of the energy shows up as this reddish constant, this differentiation here. And then we again see this periodic structure better now. So if we do the same analysis also for the bottom layer, and now we can plot the energy difference of this bottom layer Exciton and top layer Exciton here. This contrasts the charge imbalance of the layers. So if we are doping the bottom layer, the Exciton energy difference increases. And if we are doping the top layer, the Exciton energy difference decreases. And again, to visualize the structure better, I took the differentiation along this chemical potential axis. And now we clearly see the checkerboard-like pattern in this diagram. We can interpret this diagram in this way roughly. So when we see this reddish area, we are doping the bottom layer. And when we see this bluish area, we are doping the top layer. And again, we are doping the bottom layer now, and then we are doping the bottom layer now this way. So this checkerboard pattern indicates that there's a layer by a layer electron filling, telling there's some subband structure in the system. And this kind of checkerboard behaviors has been reported in the capacitance measurement of the bilayer graphene lambda levels, for example. And now we are doing this by purely optical spectroscopy. So this is kind of an optical capacitance spectroscopy. So the density periodicity of this checkerboard pattern is about 2 times 10 to the 11 centimeter minus squared. And if you think that these each line corresponds to the 1 electron per Moire site, the Moire periodicity we can estimate as 24 nanometer, which corresponds to twist angle of 0.8 degree. And this assignment of the filling, we also can justify from the magnetic field dependence of the system. So there's a question that whether there's the Barre degeneracy is broken or not. So this TMD system, we have 2 barres K and minus K, similar to the graphene. And spin digrophism is lifted, so there's a 2 degeneracy. And under magnetic field, we see a similar like phase diagram, and also this energy dependence does not change by applying a magnetic field. And that means that we cannot lift the degeneracy anymore in this system, and then justifying the assignment of the filling factor. So this is the 1 electron per Moire site. And also, we can roughly estimate the Moire periodicity from the multiple interlayer exciton fine structure, which I have shown before, and which is about 19 nanometer roughly, which shows a roughly good agreement. So now I'd like to introduce this Moire lattice model in this system. So here I show the schematic image of the TMD. So this large dot is the molybdenum atom, and the small dot is selenide atom of the bottom layer. Now I added the top layer this way. And then if we twist them, we can form the Moire lattice. And this area we show with red circles is the area where we have the alignment of the chalcogen on the top layer and the metal on the bottom layer. And here, this site, we think that the energy of the bottom layer has a local minimum on this metal site. And this light blue area, now we have the metal atom in top layer aligned to the chalcogen atom on the bottom layer. And these sites, we think that there's a potential minima at these metal atoms. So, and given that there's no tunnel coupling between two layers, we think that these lattice behaves as a kind of independent triangular lattice for each layer. So if we fill up this Moire lattice, for example, if we fill up the top layer, the electron should look like this. It's triangular lattice, and there is no tunnel coupling between two layers. And if we want to move the charge from the top layer to the bottom layer, we have to pay additional energy cost. And this we can think by simple model, for example. So by transferring charge from here to this bottom layer site here, we have to pay additional energy of this nearest neighbor electron interaction. We gain the energy by the next nearest neighbor interaction, but we again have to pay for the third nearest neighbor interaction. And in all, this energy cost is positive. And then, so the transferring single charge to the other layer costs finite energy. So this delta is the energy difference or the energy alignment between two layers. And then even if the energy alignment is zero, so this charge transfer energy is positive. So that said, if we rather moving the single charge to this side, if we move the entire charges from the top layer to the bottom layer, now we don't need to pay the extra energy. So this, from this, we can think that there should be sudden charge transfer from the top layer to the bottom layer. And indeed, we observe this sudden charge transfer in this system, which we can tell from this exciton energy shift. So this is the filling dependence of this exciton energy difference between top and bottom layer, which contrasts the charge imbalance between two layers. So at this filling of 1, if we change the electric field or the bias of the system, we suddenly change the charging configuration this way. And if we filling more or filling less, this charge transfer behavior gets smeared out like this way. And this is consistent with this sudden abrupt charge transfer behavior, which we expect from these two triangular lattices. And so here we show the actual optical spectrum of the for the case of this filling of 1. So in the left side, we have this triangular lattice on the bottom layer, and then now this right side, we have a triangular lattice of the electrons in the top layer. And we, in addition to the sudden shift of the exciton energies, we also clearly see that this attractive polaron energy, the electron resonance of the bottom layer disappears, and then now this oscillator strength fully transferred to the one in the top layer, attractive polaron, which indicates the whole charge is transferred from this layer to this layer suddenly at this bias voltages. If we go to the fitting of 2 case, and now we see a nice plateau structure in the intermediate bias voltages. This tells that there's no charge transfer in this regime, and then here corresponds to the regime where the both layers are in this Mott-Wigner state. So we have a 2 triangle lattice on the bottom layer and the top layer. And if you dope more the system or less the system, this charge transfer behavior gets smeared out again. And from the actual reflectance spectrum, we can also confirm that this attractive polaron signal also gets reduced from here to here. So this is now divided into 2 spectrum. And then if we go to this 2-0 fitting case, we fully polarize into the top layer. So our collaborator in MIT, Dr. Yan Chang and Professor Liang Fu, kindly made a classical Monte Carlo simulation for our system. And they took into account on-site repulsive energy, and then the inter-site also Coulomb interaction energy. And then they simulated this charge transfer behavior in this system. So when we have 1 electron per Moire lattice with 1 electron per Moire unit cell, we see they also reproduce a sudden charge transfer between 2 layers like this. So the lateral axis is the bias between 2 layers, and then vertical axis is the top layer filling. And then if you are away from this integer filling, and the dependence becomes smeared out this way. This sharp transition is smeared out, which is also corresponding to what we observed experimentally. So, and from these experiments, we reported that the system is now getting an incompressible state, and the charge transfer happens suddenly. And however, we didn't provide the evidence of the crystallization of the electron lattice. So here we have the idea that to detect this crystallization of the electron lattice. So if we form this electronic lattice, we will see the scattering of the exciton by this electronic lattice, and there should be a Umklapp scattering due to the periodicity of the electronic crystal. And our system is rather special because there's only weak Moire potential for this intra-layer exciton. And then without these electrons, the potential for the exciton is very small. So we will not see this Umklapp scattering. But once we have this Mott state, we will start to see this Umklapp scattering. So if we have these electronic crystals, the excitonic band structure would look like this. This is calculated by Clemens in our group. So this is the main exciton resonance, and due to the the band folding due to the Umklapp scattering, we will have another excitonic resonance here, which we call as the Umklapp exciton, which is separated about 3 milli-electron volt. The optical transition only happens around this gamma point of the excitonic band. So this is the area of the light cone. So other spectrum would not matter. So indeed, we observe this Umklapp scattering state of the excitons in the Mott-Wigner state, actually. So this plots the reflectance spectrum differentiated with energy and as a chemical potential or doping dependence of the system. So here we change the filling configuration of the top layer and bottom layer from the 0-0 state and 1-0 state and 2-0 state. So here we have a Mott state in the top layer, and then we see the Umklapp scattered additional peak here. And if we do the gauge scan in different bias voltage condition, and we see now, so here this case, we change the charge configuration from 0-0 state to 1-0 state and 1-1 state. So here again, we see the Umklapp scattered exciton for the top layer. And then now here we see the, in addition to the top layer Umklapp scattering, we see the bottom layer Umklapp scattering also. So, and these Umklapp scattered excitons tell that there is a crystal charge order in the system. And the energy splitting between this main resonance of the exciton and the Umklapp resonance is about 2.7 milli-electron volt, which is close to what they expected. And also from the bias dependence, we can nicely see that this Umklapp exciton states exists as long as the state remains in the Mott state. So this case, bottom layer is Mott state, and this case, the top layer is Mott state. And here we see the Umklapp from the bottom state, and here we see the Umklapp state from the top layer. So interestingly, we don't see the Umklapp scattered resonances for the 0-2 filling case or 2-0 filling case, but we see this for the 1-1 filling case. So it might be that the 0-2 or 2-0 state is not charge ordered. And this energy splitting here is close enough to this 1-0 case, 1-1 case, and 1-0 case, and 0-1 case is similar. So this tells that this 1-1 state is most likely just behaves as independent triangular lattice. Ah, sorry. Yeah.
We have maybe 4 more minutes and then including questions. Okay.
Okay, sorry. Yeah. Okay, I'd like to summarize my talk. And we observed the tunable coherent coupling of the inter-layer exciton and direct exciton states. And we also observed, established a charge sensing scheme using exciton polaron spectroscopy. And extending this method, we found the correlated electron state in Moire superlattice. And by finding the Umklapp excitons, we also found that the state is indeed charge ordered in this Mott-Wigner state. So the take-home message, the exciton can be now used as a probe of a correlated electron system in TMD by layers. Thank you very much.
Okay. Thank you very much, Yuya. So I would also, we have exactly 3 minutes for questions, so I would invite anybody who has a question to raise a hand or write it down. I have maybe to start with, I have a question about material sources you use. So what kind of TMD source are you using? Are these just bulk, grown, and exfoliated, or can you comment on the source of that? Because these look like extremely clean samples.
Sorry, I have difficulty to hear. So you wonder about material source or?
Does this sound better now?
Yeah.
Okay, sorry about that.
Sorry.
Yeah, I had a question about the source of material you use, because you have very clean devices.
Okay, yeah. So this one, it's not a flux grown one, and which actually we buy from HQ Graphene. And,
okay. So basically, okay. So if a flux grown one, maybe you can strongly increase the quality, right?
Yeah, I think we can also improve the quality. So yeah, I think we different to have some defect state, and then we have a bit difficulty to dope the whole side. I think this is due to the existence of defect in the system.
I see. Right, because also the question also is related. So because the group in Cornell, Kim Fai-Mak and Jie Shan, right, they're using the flux grown method, right?
That's true. Yeah.
They're using devices.
We should differently try also flux grown material.
Okay, so all right, I think we're unfortunately out of time, so probably thank you very much, Yuya. Thank you very much for the amazing talk and the amazing results. And we will then we'll move on to the next speaker. Thank you. Jose Angel, are you here?
Yeah, I'm here.
Okay, so maybe you can just start sharing your screen.
Okay, sure. Okay.
Okay. Yeah. So our next speaker is Jose Angel Silva Guillen, and he will talk about flat-dense and twisted transition metal digital gluconides. I noticed that you are from a place where Corona started, but there's no more Corona there anymore, right?
Yeah, but I'm not there anymore. So
okay,
yeah,
all right, okay.
So thanks for the introduction. Yeah. I'm José Ángel Silva Guillén. I'm currently working as a researcher in Wuhan University. And as Dima said, I think all of you know the city quite well, unfortunately. Is it working? Sorry?
Yeah, we hear you now.
Okay, sorry. So for organizing this really nice conference and symposium under the actual circumstances. So I'm going to talk about electronic properties in twisted bilayer transition metal dichalcogenides. So why study these materials? Well, basically, in the past years, there have been few studies and papers about twisted bilayer transition metal dichalcogenides, but since the discovery by Yuan Cao and Pablo Jarillo Herrero of the correlated states in a magic angle twisted bilayer graphene, there has been a boost in the experiments and the theoretical studies of this kind of twisted system. And actually, several interesting things have been found, like for example, solitons, or they have been able to simulate the Hubbard model physics in hetero bilayers and also Mott and generalized Wigner crystal states. Of course, also flat bands. They were able to detect flat bands in twisted bilayer transition metal dichalcogenides. Of course, I'm leaving a lot of papers and works here, so sorry for that. And we thought it's basically like a natural step to study this transition metal dichalcogenides after studying twisted bilayer graphene, because there are many similarities between both of them. So let me first start explaining a little bit the structure of twisted bilayer transition metal dichalcogenides. So basically, we have, as you may already know, the transition metal is sandwiched between two chalcogen atoms, and they are forming a hexagonal structure just like graphene. But in this case, in the A and B sublattices, we have two kinds of different atoms. This brings us to have two kinds of Moire cells, which can be made just by twisting the two layers by starting from an AB natural stacking, which would be the typical one that we see in nature, or an AA stacking. So in our case, we start from an AB stacking, and we just twist the two layers to whichever angle we want. And in these Moire superlattices, we basically find four positions or four regions that are high symmetry stacking. So for example, we have the typical AB stacking where the chalcogen atom is on top of the transition atom. The molybdenum BMO where the transition metal are sitting one on top of each other. The BSS where the two chalcogen atoms of one layer and the other are sitting on top of the other. And the BR, which is basically the BSS shifted a little bit. In our case, we're going to study a HOMA bilayer of molybdenum disulfide. And as you can imagine, we can do the calculations in many ways. We could do, for example, DFT calculations, but since when we lower then the twisting angle to very small values, the number of atoms that are in the system is increasingly high. And this is very difficult to do calculations with DFT. Sorry, due to the computational cost, and even with state-of-the-art supercomputers and codes, it would be quite difficult, sorry. So we take another approach, which is basically to do type binding, to use the type binding model of for transition metal like chalcogenide. So we are based in this paper that we published a couple of years ago in the group of Paco Guinea. So basically, if we look at the DFT orbital characterization of the band structure of molybdenum disulfide, we would see that we need at least 5 orbitals of the transition metal and 3 orbitals of the chalcogen atom for each of the chalcogen atom to correctly describe the
Sorry. There is no sound, sorry. Sorry. Jose, there is no sound.
Seems like his headphones are also not working.
Hi. Oh, sorry. Okay. So I don't know where I was. So where it stopped working. So basically, we're using a tight binding model, and we use this 11 orbital model, and this fitting by the group of Kashiras. And we include in some of our calculations spin orbit coupling, since the atoms are quite high, quite heavy. Sorry. So now we can plug our Hamiltonian in our homemade tight binding program, which is called TIPSY, and do, for example, normal diagonalization calculation. So we calculate the band structure of these systems for different angles, and we see that for an angle quite small, we already see some flat bands that have a bandwidth of around 20 milli-electron volts. If we lower the twist angle, we would see that these bands become even more flat, and they are detached from the valence band. We can also do density of states calculations, and basically we would see the same features. So we can sum up our calculations for different angles in this, for example, in this plot where we show that the bandwidth goes down with the twist angle. We can also see that the gap of the system is going down with the twist angle. And finally, we can also calculate the inverse participation ratio, that is basically tell us how much the system is concentrating. And this is good because and this is good because basically the experimentalists usually do STM measurements and can see how much the states are localized. We can, of course, then do local density of state calculations at the different high symmetry points that I talked in the introduction. And we can see how the flat band is localized around the BSS and the BR positions. We can also do a mapping, which would be similar to what experimentalists get with STM measurements, and we would see the same information, but in, I think, a nicer way. So we can see how the flat bands are localized in the BSS. We can do this same measure calculation for any of the angles and for any of the energy. So we would see, like, for example, the conduction band, the flat conduction band is localized in the BMO-MO positions, while the V1 is on the BSS, the V2 is more localized on the BR, and the V3 is more delocalized around the, but still around the BSS and BR positions. We can now look, as I said in the introduction, the effect of spin orbit coupling, since transition metal dichalcogenides usually are quite heavy, and this effect could be important. And for this, we look at the band structure. So when plugging in the spin orbit coupling, what we see is that although in the flat band we have no splitting, in the conduction band, a split due to the spin orbit coupling appears. And this is different from the case where you have the normal stacking, where you would see the largest splitting around the Q point. If we twist even more the system, what we would see is that this splitting becomes smaller, but it still exists. So now we can look at the orbital character and the spin character of the bands, and we can see that the spin is pinned. It's spin locked at K and the K prime with different spins at each of the points. And we think that this spin locking and the spin splitting is due to the non-negligible character of that we have px, py orbitals in these two bands over here. While, for example, in the valence band, we don't see any of this character, and therefore there is no splitting. Then we can also try to tune the electronic properties of this system, and we took two approaches. The first one was to change the interlayer distance. So basically, in these two plots here, we're taking both of the layers apart, and we see that basically nothing changes, although the valence band for really large separations are coming close together. But if we take them closer, we will see that more flat bands start appearing and separating from the other valence bands. Finally, we can also apply a perpendicular electric field, and as in the normal case where we don't twist the samples, we see how the electric field changes the gap, and how we are able to even close the gap for a sufficient large enough electric field. So finally, some conclusions. All of these results you can find them in these two works on the arXiv. I hope that I have convinced you that it seems like a natural step to study the properties of twisted transition metal dichalcogenides, and it's actually quite interesting that flat bands appear when the twist angle is low enough, and that this bandwidth lowers with the angle, that the states are localized at different positions, usually the high symmetry positions of the system, and that for most of the calculation, spin orbit coupling is important, and actually it should be included in these systems. And finally, that we are able to also tune the electronic properties. With this, I would like to thank my colleagues, Zhen and Jipei Zhang, who did most of the calculations, and Senjun Yuan, who is our supervisor, and you for your attention.
Okay, thank you very much. Do we have any questions? So yeah, I see Tobias Wolf has a question. I'm trying to unmute you right now. Yeah. Tobias, can you? Right. Okay, so here's the question. This is just a plus. Okay.
I think Bruno has a question. So he's asking me if the model includes lattice relaxation.
Right.
The answer is no. The long answer is we have just done the calculations. It doesn't affect the flat bands itself, but it does affect the localization of the atoms, the localization of the states, sorry. So it's actually quite important. And we have done the relaxations taking into account like freestanding, twisted bilayer molybdenum disulfide, and twisted bilayer, I mean the system on top of a boron nitride substrate.
Mm-hmm. Do you have any more questions? So here, Ronnie Lan is asking, are the flat bands expected to be topological as in bilayer graphene?
That I don't know. I think we should like study more the system. Like these are like just study the general properties. So to study if they are topological, I think we need further work. So sorry.
Mm-hmm. Thank you. Any more questions? Right, I think I have another question about, right, okay, so here, okay, yeah. Right, so basically I have another question about just relaxation. So is it, so if you were to just draw an analogy from twisted bilayer graphene,
mm-hmm.
Do you think you have an intuition what would happen if you include these corrugation and lattice relaxations, or is it not like really a trivial question?
Yeah. So basically so you're asking what happens if we add the relaxation, right?
Right. Yeah. I mean, do you have just from can one draw analogies from single layer from twisted bilayer?
Yeah. So what will happen? Basically, it will, as I said before, it will change not the actual shape, maybe of the band itself, or it won't change much how much the flat band, how flat is, but it will change the region where they are localized. So maybe I can wait. I have this figure because we got it basically this morning. And as you can see here, so if we don't relax the system, it looks like this. And if we relax like freely, the conduction band changes a little bit, but basically the flat band stays very flat. And if we include the relaxation taking into account a substrate of HBN, the flat band is still there. But what happens is that these states are localized in different regions.
Mm-hmm.
And that's basically it.
Okay. All right. Okay, so thank you very much.
Thank you.
And thank you very much for the beautiful talk. And then we need to move on. And our next speaker is Priya Mahadevan. Priya, are you here?
Myself? Yeah, I'm here.
Hello. Okay. Yeah, maybe you can try to share your screen.
Yeah, I've done share screen. Is it seen? Is it visible?
Yeah, it's visible. So you just need to go to presentation mode.
Yeah.
Okay, perfect. And okay, and then maybe we can just start. So okay, so Priya Mahadevan will talk about flat bands and transition matter division conjugates. When and why do we have them? Okay, Priya, please go ahead.
Yeah, at the outset, I'd like to thank the organizers for giving me this opportunity to present in this wonderful symposium. And it almost seems like an extension of the previous talk, because I'm going to be talking about flat bands and transition metal dichalcogenides. And the system of choice is again the same system. It's molybdenum diselenide. Though our approach is using ab initio calculations, we'll try to throw some insights on when and why do we have these flat bands. So since it's a symposium where the main topic has been flat bands, I just wouldn't go into depth about it, but just I want you to remember two aspects. So essentially, when we twist the two layers with respect to each other by some angle theta, what do we really have at the end of it? We usually have very large unit cells, which could be commensurate or incommensurate. And one thing that emerges is that because your real space unit cells or your crystalline, the commensurate lattices, your crystalline unit cells are very large. In reciprocal space, we have a very small Brillouin zone associated with it, with all the bands essentially folding back to gamma, and essentially flat bands probably emerging because of this significantly reduced Brillouin zone. Well, then should we even talk about a band structure for these twisted structures, or should we then view them just as a giant molecule with isolated levels in them? But let's take a step back and look at what we know about the untwisted bilayers, which have been around for a much longer time. Suppose we know that the most popular technique, which also started this field again, was the fact that you could separate them with just using a Scotch-Brite, which actually meant that you had a very weak interlayer interaction between the layers. So that a very small energy cost was involved in just separating or removing one layer from a stack of layers. This, again, using the method that I use, which is ab initio electronic structure calculations, is reflected in the band structure, which is shown in various symmetry directions. And what you see here is the monolayer band structure is shown in the red dashed lines, and the bilayer band structure is shown over here in the black lines. And essentially, they're very similar, and suggesting that the presence of the second layer merely is a weak perturbation to the band structure of the monolayer. Okay, well then let's try to understand what is the nature of the interactions. And so what we did was we took the monolayer band structure, which is shown over here for both the monolayer as well as the bilayer band structure, which is shown in the black lines, which are barely visible because we map it onto a tight binding model shown, which is overlapping these black lines shown by these red dotted lines. And essentially we have a good description for the monolayer as well as the bilayer. Here I must say that we use molybdenum D states and the selenium P states in the basis, but the radial parts of these tight binding wave functions are the maximally localized one-year functions. The advantage of this mapping is that it allows us to selectively switch off certain interactions. And what we did was, well, we took the bilayer band structure, switched off all the interlayer hopping interactions, and superposed it on the monolayer shown again here in black. And you see that we have a reasonably good description by just switching off the interlayer interactions, which suggests that the only thing that needs to be included in any Hamiltonian, which going from the monolayer to a stack of several layers, is to include the interlayer interactions between each of them. Okay, so far so good. There's another aspect that we must consider, which is, that if we just had a perfect supercell when we were, when in this whole process. And so if I took a well-known example of gallium arsenide and I plot its band structure along the primitive cell direction, and then I consider the supercell, which is just doubled in one of the directions, indeed, we have a smaller Brillouin zone over there. And as a result, we have you could think of it as a narrower band. Of course, we know that the band structure should not depend on the supercell size. And what we are seeing is an effect of band folding. And so when we unfold it out, we retrieve the primitive cell band structure. Okay, so keeping these points in mind, then let's try to reconcile the ideas to understand what's happening in the large unit cells of twisted bilayers. And in general, I will focus on MOAC2, though the ideas I feel are more valid and valid across both the molybdenum and the tungsten-based transition metal dichalcogenides. Okay, so the system I choose first, I move away from the angles which are very interesting. First, I start with an angle which is far away from the angles around 0 and the angles around 60 degrees have featured a lot in this discussion, obviously because of the rich physics that's seen at that limit. So I start with a large angle first. Let me try to understand what's happening there. As you can see, I have a large number of atoms here, around 1500 atoms. And if you want to know what the size of each primitive cell is, what the size of my unit cell in this case is, it's about 16 times each of my supercell lattice vectors or Moire cell vectors are 16 times the primitive cell vectors. So far, so good. And I carry out the same analysis of extracting out the primitive cell band structure from the supercell band structure by using this method, which is outlined in this paper by Popescu and Zunga. So essentially what I show over here is what I have taken each of the supercell band and I project it onto the K point, which this gamma to K is along the primitive cell. And I find out what is the weight at each of these points. And the width of each of these bands represents its contribution at that point. Indeed, what I see first is even in spite of having a 1500 atom very large unit cell, I have a band structure associated with it. I should have mentioned that my starting point, theta equal to 0, actually corresponds to the atom on atom AA type of stacking. So I compare the primitive cell band structure for this for this AA stacking with this what I've got for this very large unit cell for 19.03. And essentially what is shown over here is the black line is for the primitive cell. And what you can see is that in spite of the unit cell being very large, we recover the primitive cell band structure, which suggests that, well, the question is the low energy electronic structure always similar to the primitive cell one? Of course, we know that's not the case, and that's why we're all here discussing flat bands. So what exactly is happening over there? So let me go back to the angle which is in the regime where the interesting physics is, and I take a particular, the angle I choose is 3.48 degrees, which again gives me a commensurate cell with a similar, slightly larger 1626 number of atoms, and I have a large unit cell vector associated with it. As you can see, if you zoom in various regions, what you can see is, since I've started with the AA type of stacking, I have one type of stacking in this region, and over here, I have a different type of stacking. Now, let me just show it to you in a better manner. I can just focus your attention on these two stackings. This, which is AA, and the other one, which is AB prime. As you can see in the middle, you saw something like this. And if you looked at it from top, this is exactly what it looked like. As you have a staggered arrangement of the outermost selenium atoms in each layer, as a result, because of the reduced steric effects, the layers would like to come closer, and a small primitive cell, just relaxing the small unit cell gives us an interlayer separation in this case of 3.2. Whereas in this case, what you have is that it's the atom sitting on the selenium atom sits on the lower layer selenium atom. And as a result, the steric effects, they would like the layers to be as far apart as possible. And in this case, we find it to be 3.79. Indeed, when we had relaxed the structure for this 3.48 degree angle, indeed, we find variations in the interlayer separation, which varies from the AA region where the steric effects are maximum. It's around 3.74 angstroms. Whereas here, where in the center, where you have this AB prime type of stacking, you have about 3.18 angstroms. Okay, so then again, we carried out the same analysis. And what do we find in this case? What we find over here is, yeah, surprisingly, even here, you can talk about a band structure. And zooming in on the region close to the valence band maxima over here, what we find is that we have a split off band, which has a very narrow width of 19 MeV. Okay, so is it the modulation in the interlayer separation that's giving rise to all this? So, well, we just look when we just fix the interlayer separation at what is typical. I mean, for instance, in the 19.03 angle case, we had almost fixed interlayer separation, which varied from 3.42 to 3.47. So we took something intermediate, which is 3.44, and we fixed the interlayer separation for this 3.48 angle. And indeed, even here, we see that we have a band structure, and we also have a small split off band in this case too. Okay, so what is responsible for this then? What is responsible for the presence of the split off band? Well, what you see is, as I said, the coupling between the two layers is via the interlayer hopping interactions. And this, of course, depends on the selenium-selenium distances. So first we thought, let's have a profile of the selenium-selenium distances in each of the cases. And you can see that what's plotted here is how many selenium-selenium distances in these, only for these interlayer, only if the interlayer selenium-selenium distances are profiled over here. And what you can see is that there's hardly, there doesn't seem to be too much difference between the three cases we have here. So what we did was, well, let's examine the real space distribution of these distances. And firstly, so we just took the real space distribution of distances less than 3.8 angstroms. And what is shown here is, well, I join the selenium atoms in the, the two outermost layers, which have distances less than 3.8 angstroms. And then this is a projection onto the, onto the Moire cell to tell you where exactly they are located. As you can see, for the fixed interlayer separation at 3.48 degrees, I see them confined in large patches in certain regions. And what you see even for this case where I have the optimized structure, I see them the shortest distances in a totally different region. What you can see almost continuous lines over here, it's because each selenium atom in one layer is connected to 3 in the upper layer, which, those are the number of nearest neighbors that you have. So what you can immediately see, Dima was asking this question to the previous speaker, what about the character, what happens when you do the relaxation? One thing that emerges is that the character of your valence band wave function is going to be very different. Valence band maxima wave function is going to be very different in the two cases. Okay, so far so good. These were two cases where we had the split off band, and we see a feature which is this, regions with the concentrated, larger concentrated interlayer distances. And if we looked at the 19.03 and contrasted it with the 3.48 structure, what you see over here is that in the other case, you had them randomly distributed. Whereas in this case, in the 3.48 with the optimized structure, you have them in only certain regions. So this immediately tells us that the subband formation that we have in this case emerges because we have concentrated regions of enhanced interlayer interactions. So with this, I'd like to conclude with just two messages that we need structural relaxations to get the correct character of the states. And the second point is that the concentrated regions of these enhanced interlayer interactions lead to the subband formation for twisted bilayers. Although in these calculations, these were carried out at the level of GGA without any, which include correlations in a very mean field way, and not even the orbital dependence. What one could see is that since we have flat bands in this case, one could probably throw in a Coulomb interaction and have additional splittings in these levels also. So this work has been done by my graduate student, Sumanti Patra, and I briefly referred to the work by the other students. And most of the work that I've been discussing today is in this paper, which is highlighted in red, and it's submitted, and we'll put it up on the archive soon. And funding is acknowledged from the DST Nano Mission in India. Thank you for your attention.
Okay, thank you very much for the nice talk. So we're open for questions. We actually have a lot of time for questions. We have almost 7 minutes. Right, so please write your questions in the group chat. Yeah, let's just give people 10 seconds to write something down. Okay, so while we're waiting for the audience questions, maybe just a question which is slightly more general than the talk. Basically, in your case, the flat bands, they, if I understood correctly, they usually appear around 3.5 degrees.
I have considered 3.5. So the main idea that I want to indicate is that you have these regions where you have a particular type of stacking. Okay? And so basically the interlayer interactions are much stronger in that region compared to the other regions. So that's the main idea, that when you go to the large angles, you're never going to, the strain and you're never going to see only one particular type of these, these high symmetry stackings that I was talking about. It's only at these small angles or close to the, close to 0 degrees and close to 60 degrees that you'd see, because otherwise the moment you move away, every next, next layer would be moving further away. And so you never have a large enough patch, which is a particular high symmetry stacking.
And so basically, as you mentioned, like in the case of Corey Dean's work, they basically, they say it's like a continuum, right? It's a continuum of, so they have a really broad region of angles. Basically from 2 degrees to almost 5 degrees, if I remember correctly.
Probably. So it can happen. Yeah, we have, I have results here for some other angles. We also, yeah, so this is for 5.36 degrees. And even here you have this flat.
I see.
You do have it. So it's essentially in the small angle region. As you can see, just by changing from 2 to 2.5, I'm not going to be, losing this high symmetry patches. I'm going to be having that. It's only when I make the angles much larger that you have very small regions which are like AB prime or things like that.
I see. Okay, so we're just getting another question from Mahfujur Rahman. So he started writing, he's typing right now, I think. No, we can't. He asks if he can ask directly, but unfortunately we cannot unmute. So you have to type the question. Okay, it seems to be like a very complicated question. So, okay.
I can't see the questions actually.
Yeah, no, I'm like reading it up. Lenny, if he can ask him, how do we unmute him now?
Okay.
Yeah, I'm unmuted now.
Okay, good. Okay. All right.
Can you hear?
Yeah, I can hear you.
Yeah. So for this 3.5 degree, you showed different regimes with different interlayer coupling. So I assume that on these different areas, interlayer excitons should also be different, right? Hello?
Yeah. Can you hear me?
Yeah, I can hear.
Yeah, we can hear you.
Yeah, okay. Well, we haven't probed the excitons, but essentially what you can see is that okay, I don't have offhand an idea of, okay, let me just show you one figure. I don't know why I can't move my mouse up. Okay, so what you can see is this is my valence band maxima wave function for 3.48. So you can see that is okay, the region over here is my AA region, for instance. So your excitons would be probably confined, not exciton, this is only valence band maxima. So your whole wave function would be in this region. Yeah. But I can't give you offhand a number for what is the energy difference between, the levels which are localized here and the levels which are localized here to at least say what is the barrier for the holes. I don't know. But yeah.
Okay, I wanted to ask one follow-up question for that, because the reason why I was asking this question is about Stark effect. So now if you apply an out of plane electric field on different regimes, how that will influence. Can you comment on that?
Yes, the outer plane electric field would, okay. What you should realize is that there's another aspect to these structures over here. Okay, so the outer plane electric field, for instance, if I took these two regions, actually this is AB prime and this is BA prime, it's the opposite. So even they have an internal electric field associated with them. So I would probably be able to also break my KK prime symmetry, maybe, I'm not totally sure, yeah. But
Okay.
Yeah.
Yeah, that was my question.
Okay. Okay, so we are already out of time. So thank you one more time for the beautiful talk, and then we'll move on in our schedule. The next speaker is Jihua Duan. Jihua, are you here?
Yes.
Okay.
Yes. Can you hear me?
Yeah, we can hear you. And yeah, please try to share screen. Okay, we can see your screen and.
I will play it.
Okay.
Everything okay?
Everything looks good. Yeah. Okay. Yeah, Jihua, please go ahead. So you'll please go ahead. Yeah, the floor is yours.
Okay. Thanks for a nice introduction from the chairman. And my name is Jihua Duan, and I'm coming from the University of Oviedo. Today, my presentation is about the twisted nano-optics, which is might a bit different from the well-known twisted electronics. So in these three images, maybe you can briefly see that the electromagnetic mode in the different medium, like the isotropic, anisotropic, is totally different. I will explain you later. And also, if we introduce the twisted concept in the system, we will have a totally different phenomena, which is quite interesting. So this is my outline. Firstly, I will introduce you some background, and then in second part, I will introduce you our work on the in-plane anisotropic photoluminescence, and the final part would be the twisted nano-optics. So first of all, let me introduce you the Reflectance. Reflectance is a quite important definition in the nano-optics because it can provide us the solution to confine light into nanoscale. It means that we can completely break the diffraction limit of the light. And the Reflectance is something coupling the light photon with other particles, such like the free electrons in metal or doped semiconductors. If we observe the plasma Reflectance, we will see in this region, the permittivity will become negative. And similarly, in the polar dielectrics, if we couple the light to the optical phonon, we have the negative permittivity in its restaurant band, and we observe the phonon Reflectance. And since 2004, the scientists successfully exfoliate the graphene. They have found the various types of the Reflectance in the van der Waals crystals, such as the plasma Reflectance in graphene, phonon Reflectance in boron nitride, and Exciton Reflectance in molybdenum disulfide, and so on. Amazingly, if we use a technique called the scattering type spinning near field optical microscope, we can directly see the Reflectance. Such like this, in this experiment, we can put a resonant gold antenna on top of the graphene, and then we approach AFM tip quite close to the sample. We can detect the near field signal, and we can see the wavefront of the graphene plasmas propagate launched by the gold antenna, or the scientists can use the AFM tip as a launcher to launch the phonon Reflectance in boron nitride. We can map the fringes here parallel to the edge of the boron nitride coming from the phonon Reflectance. And this slide, I think I can briefly skip because I think you are all experts in the electronics. In electronics, band structure is quite important because it can provide us a lot of the information of the electrons. And if we bring two layers of the graphene and twist them, we can have the dramatically different band structure. And also at the critical angle, we can have a flat band introduce us quite interesting phenomena such as the superconductivity. So we are wondering what would happen if we bring this similar concept of the twisted in the optics. So in optics, there is one similar thing compared with the band structure in electronics. We call it the Isar frequency curve. Isar frequency curve is the slice of the claritonic dispersion in the momentum space by a constant frequency. this is the permittivity of the material. If we fix the out of plane components as the positive, we can have 3 cases in the in plane cases. If the permittivity along x and y is equal and both are negative, we will have isotropic isofrequency curve here, and also the wavefront in the real space is like the circle. But if the permittivity x and y is non-equal but both negative, we will have the elliptical isofrequency curve here. The more strongly anisotropic would be in this case. The permittivity x and y is not only with the different values, but also with the opposite signs, positive and negative. So the wavefront would be something quite interesting as the concave shape, and also correspondingly in the isofrequency curve, it would be an open hyperbola, not a circle, and you can see the pointing vector, which is always perpendicular to the isofrequency curve, is no longer collinear with the wave vector. This is a quite unique property in the hyperbolic medium. So now, what we are thinking is that what will happen if we bring two media and rotate them. So in this slide, you can show if we study the isotropic case, it's more or less the same. If we combine the 2 circular isofrequency curve, it is not so sensitive to twisted angle. But if we consider the elliptical case, or even especially the hyperbolic case, we can find the isofrequency curve should be totally completely different. But please remember that this is just a simple combination of the 2 hyperbolas without taking account the electromagnetic coupling. So what we want to show you is that what will happen if we take into account the coupling. Before the study of the twisted nano optics, we need to find a hyperbolic medium. Fortunately, we find this natural van der Waals crystal named alpha molybdenum trioxide. Its permittivity along one direction and another direction is the opposite signs. And this is the optical image of these materials. We find that if we launch with the AFMT, the photoluminescence should like the concave wavefront here, and the experimental extracted isofrequency curve is exactly the open hyperbola. So the molybdenum trioxide provides us an ideal platform for studying the twisted nano optics. But before the study, we need to fix another problem, because the molybdenum trioxide is a brandly new van der Waals crystals. We don't know the permittivity, which is quite important for the study. So we developed this method. We combined FDIR and the near field measurements to extract the accurate values of the permittivity of molybdenum trioxide. It should be noticed that if we only use the FDIR, because the molybdenum trioxide is quite small, maybe the signal is quite weak, and also the FDIR is not so sensitive for the imaginary part of the permittivity. But if we combine far field and the near field measurements, we can extract the accurate values for both the real parts and the imaginary parts. We published this work in the Advanced Materials this year. And another question we need to solve is the analytical solution, because previously we can only solve the equation in the uniaxial crystal, but the molybdenum trioxide is a biaxial crystal. So we developed this matrix for describing the electromagnetic modes in the biaxial crystal. We simplify them into this beautiful equation. With this equation, we can analytically calculate the dispersion of the photoluminescence as this dashed line. And you can see it's matched quite well with both the experimental and the numerical simulations. So until now, we have everything prepared for study of the twisted nano optics. So I will show you what will happen if we take into account the electromagnetic coupling. before the measurements, we conduct the theoretical study. We use a dipole to launch the phonoplaretons into molybdenum trioxide layers. If the twisting angle is 0 degree, we can see the wavefront of the phonoplaretons is more or less like the concave and also open hyperbola in the K-space. This is quite similar with the one in molybdenum trioxide crystal. But if the twist angle is 30 degrees, we observe the wavefront and also the Eiser frequency curve tilted a bit. And more interestingly, if we further increase the twisting angle to 90 degrees, we observe the wavefront is completely different from the this case, because it becomes the enclosed wavefront and also the closed Eiser frequency curve here. So that means we change the Eiser frequency curve from the open to closed. We observe a topological transition in optics. What we are wondering now, what will happen at exactly where the topological transition occurs. So at this twisted angle, 63 degrees, we find that the Eiser frequency curve becomes totally flat. And that means the energy, all energy of the propagation of the phonoplaretons only along one direction. So this is quite important because it can provide us a method to guide the energy at the nanoscale along one special direction. So besides the theory, we want to realize it in the experiment. In theory, we use a dipole, but in experiments, we need to use the resonance gold antenna to map the wavefront of the phonoplaretons. Here I show you the experimental results. If the twist angle is 30 degrees, we observe the tilted wavefront and also tilted open hyperbola at the Eiser frequency curve. The experimental results match well with the numerical and the theoretical calculation. And similarly, if the twist angle is 90 degrees, we observe the closed wavefront and also the Eiser frequency curve. So experimentally, we also observe the topological transition here. And more interestingly, I show you here, we call it the magic angle or the critical angle. At this angle, we exactly find the canalization of the phonoplaretons here. We can see the phonoplaretons propagate only along this direction, and in the experimentally extracted Eiser frequency curve, it becomes also flat. So this means it provides us a method to guide the energy of the phonoplaretons only along one direction. Besides the twist angle, we find another parameter to have the influence of the Eiser frequency curve, because if we use the instant wavelength, smaller instant wavelengths, the two open hyperbola is quite far away. We more or less we have the open Eiser frequency curve. If we further increase the instant frequency wavelengths, they are getting closer, and finally we will have this intersecting point, and we will have the closed wavefront and also the Eiser frequency curve. That means this is another topological transition. It's controlled by the instant wavelength from the open to closed Eiser frequency curve. Another important thing I want to show you that because we know this is in the canalization regime of the phonoplaretons, that means that there should not be geometrical decay of the propagation in this regime. So we extract the line profile of the canalized phonoplaretons and also the common phonoplaretons. We find the geometrical decay factor for canalized phonoplaretons is 0. That means we don't have the geometrical propagating decay of the canalized phonoplaretons. It provides us quite great potential to have the highly guided nano light at the nanoscale with low loss. So the twisted nano optics, I have to say, is quite new, but a vibrating field, because almost at the same time, there are 4 papers published in the different journal to describe the similar thing, and also there are other papers published to describe the more Exciton. So I hope this interesting phenomena can grow can attract more attentions, because this indicates us that the twisted concept is not only important for electronics, but also quite important for nano-optics. Finally, I want to thank you, our quantum nano-optics group in University of Oviedo, and especially I want to thank you, my supervisor, Pablo Alonso Gonzalez, and other people in our group, and also our collaborators in BIPC and ISP for their theoretical support, and also the fabrication of the gold antennas. Of course, thank you very much for your attention. That would be all.
Okay. Yeah, thank you very much for the amazing talk. So I think it's really fantastic that this concept of magic angles also applies to many other systems, which can in particular be studied with optics now. Okay, so the floor is open for questions. Please type your questions. Right. So Tobias Stauber has a first question. So he's asking, what defines the magic angle theta 54 degrees? Are those the materials constant? It does not seem to be Moire physics.
Okay, this is actually a quite good question, because I think I need to explain a bit, because this thing, what I show you is totally different physics compared with the Moire physics, because this is something like the two anisotropic electromagnetic mode, the coupling. What the physical mechanism behind them is just the electromagnetic coupling, not related to the Moire physics. So we define this magic angle is just to have the angle at which we have the flat band Isar frequency curve, and we have the canalization of the phonopolarity.
And I also have then the question about the name magic angle. So basically, in graphene, the magic angle means that there is some really diverging region which gives you a flat where the energy dispersion diverges, right? Where we get the flat bands. And here, kind of a magic angle means something completely different, right? So it's not conceptually.
Yes.
Is this a new name? Is this a new name? The magic angle, or were magic angles already like in photonic in the phonopolarity that were known before?
I think this is a quite new concept, because before, I think we can also call it critical angle if you feel uncomfortable about that definition, because previously we didn't observe any flat band in the peritonics, but only those 4 papers is quite friendly new in this year. So maybe we can call it the critical angle.
Yeah, no, I mean, I think that like this Andrea Lu paper, it calls it photonic magic angle. Then somehow it already it already defines a slightly different meaning to that, right? Okay, so any more questions? Maybe we have one more question, but other than that, we are almost out of time. Okay, I think thanks, Jan. Thanks very much for the very nice results and sharing with us. And we then move on to the next speaker.
Okay, thanks.
Okay, thank you. And the next speaker is Alejandro Gonzalez Tudela. Are you here?
Yes, I'm here.
Okay. Okay. So Alejandro will speak about simulating twisttronics of ultra cold atoms. So even more a different twist. How to use this concept of Moire physics in a different system. So Alejandro, please, the floor is yours.
So yes, you can see my screen, right?
Yep.
Okay, so thanks for the introduction, Dima. Today I wanted to talk about a different twist. So we wanted to tell you, it's about a work that we did recently with Ignacio Cirac, and it's about how to build synthetic twisted bilayers using ultra cold atom systems. It's a different system of study. So the motivation, well, the motivation is, well, we all know, I mean, there was even though the physics of twisted bilayers was studied longer, I mean, the field exploded with these experiments by the group of MIT, where they observed this unconventional superconducting and strongly correlated insulating behavior. And nowadays there are many other groups that have reproduced and improved these observations and also explored different, concepts. But I would say that even despite all this experimental and theoretical work in the field, there are still some challenges, both experimentally and theoretically. On the theoretical side, I mean, what makes these systems interesting, that is the fact that they are strongly correlated, so that the tunnelings, the effective tunneling in these new Moire cells are of the order of the on-site energies, make these systems also very difficult to study. I mean, it's kind of trivial statement, but it's difficult to study. Also, the fact that this magic angle behavior occurs for such small angles, like of the order of 1 degree, make that the Moire cells are huge. So they are 10 to the 4 lattice sites in units of the individual graphene layers. And this makes ab initio descriptions very challenging, so that you need to work out on effective models, how to capture the physics properly. This also makes structural relaxation effects more important, and you need to include it in your model. And it complicates overall the description and also probably the experimental overview. And also, I mean, I would say that there are, even though there are many experiments now, and you can put pressure, you can move the temperature, the gate voltage, solid state systems have certain parameters that are difficult to change. Like, for example, and in particular, the one that motivated me most was the inter-layer hopping compared to the intra-layer one, that, for example, in graphene, I think it's of the order of 10%. And basically there's some tunability that, that you cannot do with this kind of systems. And at this respect, you have like two alternatives, I would say. So one is to improve basically 16 samples, improve the setups to measure different things and so on. And I mean, there has been many experiments in this direction, and they actually have improved a lot already with respect to the initial observations. But the other alternative, and it's the one that I try to advocate in this talk, is how, try to build synthetic systems that, try to reproduce maybe not all the behavior of the solid state analogs, but at least that capture some of the features and that you can be used to learn things from this solid state environment. And well, the one that I will advocate is this ultra cold atoms in optical lattices that maybe here there's some people that is not familiar. So what people do in this system is a quite well-established quantum simulator platform. So they send counter-propagating lasers in free space. They create an optical potential through the interference of these lasers. These lasers are off resonant with a given optical transition of an atom. And this creates an arXiv that basically allows to trap the atoms in this minima here. And this system is very powerful as quantum simulator because basically the geometries are very tunable. So if you change the laser configuration, you can go from a square to hexagonal, triangular lattices. By changing the tuning of the laser frequency and the intensity of the laser, you can increase the lattice depth. And this basically makes that the atoms that are hopping here will be tunneled faster or slower. Also, you can tune even the nature, so you can use, depending on the atomic isotope, it can be fermionic or bosonic, and also the interactions can be tuned. There are these things like phase-back resonances, but basically the atoms, when they are on top of each other in the same lattice size, you have some local energy penalty. So basically they are very well known for being well simulators or Fermi and Bose-Hubbard models, so these kind of things, and everything is very tunable. In fact, there has been already experiments that playing with different geometries, they have been able to simulate Dirac points to build, there is this paper by Leticia et al. In 2012, where they were able to simulate Dirac points in this with fermionic atoms, somehow to simulate artificial graphene. And what we wanted is to give a new twist and trying to build basically a system based of fermionic ultra-cold atoms that can basically mimic the behavior of these twisted bilayer systems. And the key ingredient that we use is what people call in this field state-dependent optical lattices. And the idea is pretty simple. I mean, what happens in atoms is that you don't have typically a single optical transition, but you can have many because you have the nuclear spin that couples to the electronic one, so you have an hyperfine structure. And the ground states are split in the hyperfine structure, so you can have many levels. And then playing with magnetic fields, you can split them and you can play with the laser frequencies. And you can make basically traps that are dependent on the atomic state of your atom. So that if the atom size basically has a given atomic state, it feels a different trapping potential that if it's in the other atomic state. And what is the advantage of this? And what we wanted to do is that if you have two different types of atoms, I mean, basically the interlayer tunneling will be controlled by the depth of these trapping potentials that is controlled by these lasers. And then you can add additional lasers to make a Raman-assisted transition to couple these two. And then you can tune the intra-layer hopping in a different way from the intra-layer one. So you can have more flexibility at this respect. In particular, so well, we spent a lot of time in the paper to see how one can do it. Our proposals is based mostly in alkaline earth atoms. These are we think the more suitable for doing that. These alkaline earth atoms like ytterbium, strontium, so they are very special because they have 2 electrons in an outer S shell. And basically what it gives rise is that you have an optically excited state with a double spin forbidden transition. So this atom basically have a very long lifetime in this excited state, and you can use it as basically as a metastable state. So if you place the atomic excitation here, it will remain there. It will be able to hop and simulate one of the bilayers, one of the layers of the bilayer, and it will be able to live for long. So this is, I mean, basically the main ingredient that we use, and the advantage is that because these atoms are separated by optical frequencies, you have a lot of flexibility to engineer the potentials, and that's the main advantage. Then we propose, maybe, I mean, this is a bit technical, but basically we propose a configuration in which basically, instead of doing, I mean, typically if you want to create, for example, a square lattice, you will put the mirrors on top of each other, and you will have a square lattice. What we do is that you physically rotate these mirrors, and then you create this twisted potential. And in order to make basically this red and the blue potentials different that will simulate the different twisted optical potentials, what we put is what is called a half-wave plate. It's just a passive element that switches the polarization of light from being in plane to out of plane. And this creates basically a 2 orthogonal electric fields that they don't interfere. And then the only question is how to harness this thing in such a way that you create these state-dependent optical potentials. And well, I don't want to enter a lot into the detail because I don't have time. I wanted to explore better more the physics that can emerge in these synthetic systems. But basically we propose 2 ways. One is harnessing the fact that these atoms also couple to the nuclear spin. You have hyperfine multiplets that you can split with the magnetic field and harness these potentials to create these twisted bilayers. Also, the other one is what people call these tune-out wavelengths, that basically, well, people know that for these atoms, there are certain wavelengths in which the polarizability of this atomic state, and therefore the potential that you are creating is 0, while the other one is not 0. So basically, this allows you to create, basically, for these 2 wavelengths, independent potentials for the 2. And the only thing is that you have to correct because they have different wavelengths, you have to put an angle in one of them so to correct the different periodicities if you want to have equal layers, but that's also very simple. And all the details are in the paper, so you can ask me afterwards. But what I wanted to talk more, because I wanted to give you the feeling of the motivation of why this could be interesting, is to talk a little bit about the emergent physics. And we started illustrating it with the square bilayers, as well as different, so we don't have a Dirac point here. So in these square bilayers, there are a slightly different commensuration angle where these Moire patterns occur. And we made a simplification in that paper to make the calculations. That was that if you basically make a very deep lattice, you can make that the atomic wave functions are very localized in the minima. And then you can simplify the tunneling intra-layer to be in nearest neighbor and a local interlayer hopping. And this I will tell you afterwards what happens if you relax these conditions. And also we focus on because our motivation was to see if you can have interesting physics at large angles compared to this magic angle behavior that occurs at very small angles. And this is the kind of things we plot. For example, you can plot, we took the largest commensurate angle for this square bilayer, which is 37 degrees. So this would be in red and blue, the two bilayers. The unit cell in this case is just 5 by 5, if I remember correctly. And then you see that what we plot here is the density of states as a function of the interlayer hopping compared to the intralayer one. So this is the ratio, so we vary it. And you go from a place where the two layers are uncoupled, you have a single Van Hove singularity, typical of square bilayers. And then as you start increasing, you see that new structure emerges. So you have the splitting of Van Hove singularities that also occurs in graphene. You have some asymmetric Van Hove singularities. And also at some critical detuning, also you see that you get a splitting of the two isolated bands in the upper and the lower part of the spectrum. And in fact, if you study the behavior now with what happens if you decrease the angle, you can study, for example, what happens with this isolated band as the angle decreases for a fixed interlayer hopping that is large. And you see that also becomes narrower, like what you would expect. As you increase this parameter m, the angle is becoming smaller and smaller, and you get narrower and narrower bands. So that's one thing. You see that as it happens also in magic angle graphene, so you get, if you study more in detail what is the density of a state, you see that you get these asymmetric Van Hove singularities that basically resemble to these higher order Van Hove singularities that also appear in twisted bilayer graphene that has to do with the degeneracies of these bands, of this projected band structure. And we also studied, for example, now with hexagonal twisted bilayers, what happens there, also for large angle, like 21 degrees. And you see that if you increase the interlayer hopping, I mean, even at that large angle, you are able to isolate these two bands around the Dirac point. So basically, so you can get this thing. So we didn't observe that yet for this model, this magic angle behavior that the bands become flat. And what we were doing now was basically to introducing, making improvements to this simplified model, allowing for longer range hoppings, with the motivation basically of trying to find this magic angle behavior at larger angle. But actually, there was some paper that appeared actually 1 month ago that actually somehow scooped us a little bit, that they were basically doing that. So they took our proposal. So they considered these hexagonal optical lattices with pseudo-spin states, with this state-dependent optical lattice. And they found actually that if you do the calculations for small angles and taking into account longer range hoppings, you see that at all twist angle below 6 degrees, the system can become magic in the sense that there is a critical interlayer versus intralayer hopping that actually the things become flat. There is a narrow flat band in the middle. So that's actually one of the motivations that we had to study these systems. Also another motivation, let's say more from the experimental point of view, and if you are able to implement it, is that if you are able to measure with this quantum simulator very well controlled, you can discard certain mechanisms that has been proposed to explain the unconventional phenomena. Like for example, we will not have phonons, electron-phonon coupling. So if you get this, I mean, you can discard all the things that happen because of this. Also, I think that another asset is that you have different ways of probing the systems. So what we did, because of my background that is quantum optics, what we studied was what happens now if you put a defect atom here and couple to this twisted bilayer system. So it's like what I put here, like if it was a quantum emitter, it's similar to this SNOM configuration that the previous speaker was mentioning. And then you see that you get very anisotropic emission of matter waves now because we have atoms here. So there will be matter waves that are propagating along the directions of the unit cell. If you look at how this artificial emitter is decaying, so you have a strongly non-Markovian emission. So I don't want to enter a lot into the detail, but basically this feeling that you can have different ways of probing the system. And also another thing that I wanted to do was to explore the role of non-local interactions in all these phenomena, because we have a recent implementation. I mean, typically I told you that in cold atoms, the interactions are local. Typically they only interact when they are on top of each other. And then what we made in this nature was to give a proposal to have longer range interaction actually in the even Coulomb-like. So we propose it for quantum chemistry simulation. So I wanted now to investigate, to combine these two ideas of this synthetic twisted bilayer with these non-local interactions to see what kind of physics emerge from this. So with that, I wanted to give you like just the take-home messages. So the first one is that you can build synthetic twisted bilayer using these alkaline earth atoms. And that they can be used as a platform, alternative platform to study twistronics that give you access to a novel parameter regime and novel ways of probing. I also refer to this, there was after our paper another paper by the group of Levenstein where they proposed an alternative way that did not imply rotating the mirrors, just using synthetic dimensions, but it's basically a very similar idea. And it's very nice. And with that, I wanted to acknowledge my collaborator, Ignacio Cirac, and thank you for your attention.
Okay, thank you very much, Alejandro, for the very nice talk. So the floor is open for questions. Again, please type the questions, or actually we opened also the unmuting microphone, so you can actually just go ahead and ask questions. Okay, so again, Tobias Stauber has a question. How large can the optical lattice be? How many lattice sites can you generate?
No, that's a very good question. I think that the actual numbers now are, let's say in 2D, probably 100 by 100. I think I know people in MPQ in the Max Planck Institute, they are trying to, I mean, the main problem there is that typically you have not a flat potential, so they create these 2D potentials, and then they have a parabolic dispersion, and this alters a little bit. So they are trying to build these systems within cavities to make these things bigger. And then the systems, I mean, that they are targeting is 1000 by 1000. Also, one thing that you need to take into account is that I think that one of the main advantages of this thing is that if we can find physics at larger angles, no? So we don't want to target unit cells of 10 to the 4, 10 to the 4. This will be impractical for cold atoms. So I mean, like in this figure, like of the square bilayers that I saw, the unit cell was 5 by 5, so it was pretty small.
Okay, thank you. And then another question by Carlos Anton Solanas. When would the bilayer system of a given size become computationally challenging to simulate? What would make the difficulty to theoretically predict it? Is it the size or is it the interaction control?
Well, it depends what you, I mean, so if you mean like just numerically or in the experiment, I mean, so let's say for the
the first possible question is computationally challenging to simulate.
Well, I think, I don't know, like people do have initial, I mean, there is people probably that know more than me, but so my understanding was that this huge, I mean, this 10 to the 4 is already within the limit of what people can calculate. I mean, it's this magic angle. And regarding the experiment, I think that there is not the complication is how to build them like in a robust way, these things without disorder and so on. But I think that the limitation basically there is what Tobias asked, is how large can you make the system more than the challenges. That this is what will limit the experiments in the end.
Okay, thank you very much. We have another question by Leni Bascones. So if interactions between the atomic orbitals are not 1 over r, maybe the physics is also different.
No, actually, yes. I mean, this is one of the things. Maybe actually, at some point I wanted to visit ICMN and talk to the people there that is doing this physics, because I mean, one of the things that I want to study is precisely this, because we have a way of engineering not only 1 over r interactions, but I mean, we can engineer different non-local potentials. And I would like to, yes, I don't have a lot of intuition because I still didn't study, but I think it could give rise to, yes, it's an interesting thing to look, because we can really have the flexibility now of creating different, let's say, interaction potentials. I don't know. So the answer is I don't know yet, but I think it's an interesting question to look at.
Okay. Okay. So we're close to the next session. So thank you very much, Alejandro. So we'll move on to the next speaker. And the next speaker is Anna Pertsova. Are you here, Anna? Hello? Okay. So we see that you put your screen, but we cannot hear you. Can you maybe check your microphone?
Yes. Can you hear me now?
No, yeah, now we can hear you.
Okay. I just have to
Okay.
plug it in
Okay.
one more time.
Right.
Yeah.
So, okay, Anna. So I think I'll just open the floor for you.
Yeah. Thank you so much for the opportunity to present here. So I will talk about the work that was done at in the group of Sasha Balatsky at Nordita, and it is about Dirac node engineering and flat bands in doped Dirac materials. So I have to say that this might not be so much relevant to Moire physics, because here we are considering actually impurity bands in Dirac materials. Nevertheless, we found some interesting features that connect the flat impurity bands with nodal structure in topological insulators and other Dirac materials. And so we thought these are quite interesting features, and that it would be nice to share in this symposium. So just to start with a brief motivation, what made us look into this. So the main theme here is that electronic structure of Dirac materials, and in particular topological insulators, can be manipulated by impurities. And of course, the most obvious example is the quantum anomalous Hall effect, which is observed in thin films of magnetically doped three-dimensional TIs. So in this simple picture, if we take a TI and we dope it with magnetic impurities, then we hope that the impurities would would form a magnetic order, and a gap would open in the surface Dirac cone. That would lead to chiral edge states in the whole bar geometry, and this would lead to the quantum anomalous Hall effect. In reality, this picture is actually a bit more complicated, because the impurities not only have the magnetic moment, which acts as a effective exchange interaction, but they also have potential. They also induce potential scattering, and so when this potential scattering is taken into account, we will see that impurities actually induce resonances, which we call impurity resonances, that appear on top of the Dirac states. In the ideal case of a Dirac dispersion, the position of this resonance is inversely proportional to the impurity potential. So this picture has been kind of advocated by Balatsky and collaborators, and if both magnetic moment and impurity and potential scattering is taken into account, we will see that actually these impurity resonances, they interfere with the magnetic gap. So in fact, they can appear inside the magnetic gap, and this kind of provides an explanation why in many experiments there's actually no clear gap. There is a suppression of the spectral weight around the original Dirac point, but there are also these resonances that appear in the experimental spectroscopy images. So we have been kind of looking into this impurity resonances in different settings using model calculations and also ab initio calculations, kind of to show how they appear in realistic systems and how they depend on the nature of the TI and the nature of the magnetic doping. And when we were while we were looking into these features, we actually found that that even non-magnetic impurities can modify dramatically the electronic structure around the Dirac nodes. So if you look at periodically arranged impurities, which is often done in this kind of calculations on doped TIs, then we'll see that impurities create sort of localized bands, which appear as peaks in the density of states. And the way, because of the hybridization of these bands with the Dirac states, we can actually have the nodal structure is modified. So we can actually have splitting of the original Dirac nodes, and we also can induce new Dirac nodes that were not present in the original structure. And this is a kind of feature that I want to talk about today. So we take a multi-orbital tie binding model for a typical topological insulator, and we put an impurity, we take a thin film and we put an impurity in the top on one of the surfaces of the film. And this graphs show the calculated spectral function resolved as a function of the distance from the surface where the impurity is located. So on the left is the spectral function at the surface, and this shows that there is an impurity band, and the Dirac node is actually split into two. While this picture here shows the spectral function on the bottom surface, which is not affected by the impurity. In the band structure calculations, we actually have the superposition of the two, because we have the bottom Dirac cone, which is not affected by the impurity, and it still has a Dirac node, and we have the top surface bands, and it is clear that there is a splitting of the Dirac node, and also, excuse me, and also there is a new Dirac point, a Dirac node appearing at the edge of the brilliant zone. This particular situation happens when the impurity resonance falls exactly at the energy of the Dirac node. If we look at the evolution of the electronic structure with impurity potential, we start with a pristine case, and then we switch on the impurity potential, and we see that the impurity band emerges from somewhere from the valence band. And as we increase the impurity potential, it moves to the energies close to the Dirac node, inducing this splitting and additional node that I already mentioned. And as the impurity potential is increased further, the resonance moves away from the Dirac point into the conduction band. If we focus on this particular situation when the impurity is at the impurity resonance is exactly at the Dirac node, and we can show that the splitting of the original Dirac node depends on the concentration of the impurities. So if when we decrease the concentration, the splitting decreases and the impurity band flattens out. It can be shown that the splitting goes as square root of the impurity concentration. So how can we explain this splitting? So if we take a simple model of the Dirac state and couple it to a impurity band. So this is the Hamiltonian that describes the situation. So we have a TI Hamiltonian, which is simply K dot sigma and the impurity band, and V is the hybridization between the two. So the impurity band can be anything. We can give it a curvature, so it can be a parabolic band or it can be a flat band, as in the bottom panels. Because of the spinor structure of the Dirac-Hamiltonian, the Hilbert space is 4 by 4, so the impurity band is actually doubly degenerate. So we have 4 bands, and when the impurity band hybridizes with the Dirac states, the bands have to reconnect somehow, and the way that they reconnect is shown here. So when the band approaches the Dirac point, we get this structure in which the nodes appear to be split. If we calculate we simply diagonalize the Hamiltonian, we get the analytical expressions for these states at the gamma point. We see that the splitting is exactly given by the hybridization between the impurity band and the Dirac-Hamiltonian. So this simple model kind of explains the features that we observe in the more complicated die-binding model. So it might look like this might be just an artifact of the supercell calculation, where we have this periodic arrangement of impurities and flat bands, impurity flat bands. But in fact, this feature has also been seen in other type of calculations, which take into account disorder. So this plot here, the black with the black background, this is from an earlier work, which also looked at impurities on the TI surface using Green's functions approach. Here, the focus was actually on the role of the magnetic moment. So. So the main point here what happens to the Dirac node when we increase the magnetic moment. However, another feature also appeared in these calculations and was somewhat overlooked, is the appearance of this fuzzy Dirac node when we increase the impurity potential, the scattering potential. And this picture looks very much similar to the band structures that I showed you before. So actually this feature also is present in calculations that do not necessarily require periodic arrangement of impurities. I've also found other works that where such features have been seen. For example, for a heterostructure of topological insulator and normal insulator, the valence band of the normal insulator kind of plays a role of the impurity band, and it hybridizes with the Dirac states, and has been shown with model calculations and DFT calculations that the splitting of the Dirac node can be induced when the bands are aligned in such a way that the external band is exactly at the original Dirac node. Something similar was also seen in non-perturbative Green's function-based calculations for vacancies in graphene. So these calculations actually show the splitting of the Dirac node and a flat band emerging at the same energy. So the question that might be interesting to ask is whether we are doing something to the topology of the system, because we're kind of splitting the nodes, and as I also mentioned, we are inducing additional nodes at the edges of the Brillouin zone. Does it mean that we somehow change the topology with simply doping with non-magnetic impurities? Well, we don't expect that, since time reversal symmetry is preserved, but it's interesting to see what happens exactly. And to analyze this, even without going into calculation of topological invariance and proving this point rigorously, we can use this kind of phenomenological argument that was originally proposed to distinguish trivial insulators from topological insulators. So in a topological insulator, between any two time reversal invariant momenta, odd number of edge states to cross the Fermi level, and there is this partner switching behavior. In the pristine topological oscillator with one Dirac cone, this is obvious. Whenever we place the Fermi energy inside the bulk gap, there is always one edge state crossing the Fermi level. Now, if we look at the schematic of the band structures that I showed you arise from that from our time binding calculations and also DFT, is that in the presence of the impurity resonance exactly at the Dirac point, we have this structure here with two nodes split and an additional node at the Brillouin zone edge. Now, still, if we put a Fermi level anywhere between the two time reversal invariant momenta, anywhere inside the bulk gap, you'll see that there is just one edge state, one mode crossing the Fermi level. It's also clear that time reversal symmetry implies Kramer's degeneracy at time reversal invariant momenta. In this case, the time reversal invariant momenta are the three inequivalent M points, which are exactly the corners at of the Brillouin zone. So it is not surprising that we have an additional Dirac node at the M point. So now we have the only difference with the pristine situation is that we now have actually two nodes plus 4 is actually 6 nodes in the whole Brillouin zone. Now another quantity that we can assign to these Dirac nodes is the helicity, the spin helicity. If we look at the winding of the spin in momentum space for each of the TI surfaces, we can assign a particular helicity to them. So for example, for the top surface, the upper Dirac cone has a spin momentum lock in this direction, let's say clockwise. The upper Dirac cone has the spin momentum locking in the opposite direction, and we can assign helicity +1 to this situation. For the bottom surface, the spin momentum locking direction is reversed. We can assign helicity -1. So in the pristine TI slab, freestanding slab, which has top and bottom surfaces, we have helicities +1 on the top and -1 on the bottom. Then now moving to our situation with the impurity band hybridizing with the Dirac cone, we kind of calculated the helicity, the spin, the winding of the spin for each of these new Dirac nodes, and we found that overall the helicity of the top surface is the same as in the pristine slab. So it's actually topological properties have not changed, but the bands reconnected in a peculiar way to accommodate for this. Now, does it have any implications for experiment? Could these features be somehow detected in experiments? Well, of course, it's having periodic arrangement of impurities quite an artificial situation, especially for TIs. But as I showed you, this particular feature of the splitting of the Dirac node due to the impurity resonance is actually present regardless of whether we have an ordered lattice or a disordered lattice. So in principle, it should be accessible in RPS or STM experiments. Also, if we want to think about more realistic examples, one example that we thought of is our superlattices of organic molecules that are known to be possible in graphene structures. So these are self-organized kind of periodic lattices of organic molecules on graphene. So maybe one could look into these features there in these systems. more talking about flat bands and nodes, it's of course it depends on the parameters of the system, whether the impurity resonance actually happens at the Dirac node in a realistic system. It depends on the kind of impurities and the host, and it also it's not necessarily that the Fermi level happens to be at the relevant energy where the impurity band is. So these features somehow have to be adjusted in the experiments. For example, one possibility if to move. Yeah.
And so sorry, we're basically out of time. So
okay, I'm just finishing here. Yeah, just one minute that I wanted to mention that there wasn't actually an RPS experiment that we think might have detected this Dirac node splitting in their setup for a chromium-based bismuth selenide TI. And there are also some indications that by tuning the RPS setup, they were able to see a little bit of the flat band as well in the system, which manifested as a extended spectral weight near the Dirac cone. Yeah, so this brings me to my conclusions. What I showed you is that it is possible to engineer nodal structure and flat bands and these additional fuzzy Dirac nodes in impurity dope Dirac materials. And one topic that we're looking at the moment, is the influence of interaction. So it's actually we are looking at how the impurity bands and the Dirac bands are renormalized by interactions on the impurity sites. Yeah, that's it. Thank you very much for your attention.
Okay, thank you very much, Anna. Sorry, we're out of time. So
Sorry
really
for
enjoyed your
taking too
talk,
long.
but yeah,
Yep.
no worries. But we move on to the next speaker, who is Glenn Wagner. Glenn, are you here?
Yep.
So don't worry, we're 2 minutes delayed, but I'll try to make sure that to give you 2 minutes extra in the end.
Okay, can you see the
You can see the screen,
the
yeah?
screen?
Yeah. Okay, Glenn, the floor is yours.
Thanks. So I'm going to be talking about domain walls in twisted bilayer graphene. And first of all, I'd like to thank my collaborators on this project. So the two PIs on this project were Steve Simon and Sid Parameswaran. And we also had a master's student working on this, Nilad Pal. And most of the heavy lifting was done by Yves, who's a PhD student at Oxford and also gave a talk yesterday. So let me dive right in and say that we're thinking about HBN aligned twisted bilayer graphene close to the magic angle. And so of course, this is famously described by the continuum model developed by Bistitzer and McDonald, which gives you these two flat bands. And now when you align the graphene with HBN, so this opens up a gap in the band structure. So HBN has the same hexagonal structure as graphene, but with two inequivalent atoms on the two inequivalent lattice sites. And so this acts like a staggered sublattice potential. And because one of the bands is mainly localized on one sublattice, the other band mainly localized on the other sublattice, when you apply the staggered sublattice potential, it opens up a gap. One band gets pushed up in energy, the other band gets pushed down in energy. And these bands have opposite Chern number. So in addition, these two bands are each fourfold degenerate because of the spin and Vallée degrees of freedom. And so this gives us a total of 8 flat bands that we can fill. So we were motivated by some experiments that were done at filling +3, meaning that we work at a filling where 7 of these 8 bands can be filled. And so there were experiments by 2 groups, Andrea Young's group and David Goldhaber-Gordon's group, and they observed the quantized anomalous Hall effect in the system. So here in this plot from Andrea Young's group, you see that the Hall resistivity is quantized in units of h over e squared. And so this was understood using some Hartley-Fock studies. And basically at this filling of +3, we can fill 7 out of these 8 bands. And because of the usual argument for exchange interactions favoring ferromagnetic states, we end up with 7 of these bands completely filled, 1 of these bands completely empty, and this gives us a net Chern number, which leads to this quantized Hall response. And so this is all fairly well understood at this point. And all of these Hartley-Fock studies were done for uniform systems, but what we were interested in looking at is what happens when you have domains, and what happens in these sort of inhomogeneous setups. And there's been some experiments on this as well. So this is from Andrea Young's group. And this is a picture of one of their devices with a plot of the magnetization as a function of position. And indeed, you see that the magnetization as a function of position isn't uniform. And so these are hints that we have domains in the system. So we then started thinking about what the different possible types of domain walls are. And to do that, let us take our 2-dimensional system and consider splitting it into an X and a Y direction, and consider a domain which is somewhere on the left of the system and a domain somewhere on the right of the system. So we also need to say what the substate is doing as a function of this X coordinate. So first of all, let me just consider a uniform substate, and later on we'll consider a step substate. So delta of X is just this staggered sublattice potential. And because it's constant as a function of X, the band structure is constant as a function of X as well. So this is shown down here. We have these 4 bands. I'm leaving out spin for simplicity. So we just have 4 bands, and let me work at filling -3, meaning that we fill up 1 of these 4 bands. And we see that the ground state, of course, is just filling up 1 of these bands completely on the left and the right of the system. And so I've labeled these bands by the valley and the Chern number. And so on the left, we occupy valley K Chern number +1, and on the right, we occupy valley K Chern number +1. But of course, we could have done something else. We could have considered the setup where we have valley K Chern number +1 filled on the left, but valley K primed Chern number -1 filled on the right. And so we have these 2 domains with a domain wall in between. And we call this type of domain wall the intertwined wall, because we have this intertwining of valley and orbital degrees of freedom across the domain wall. Both the Chern number and the valley flip. And so the interesting thing that we found about this intertwined wall in our Hartley-Fock study of this problem is that it actually gets pinned by the Moire potential. So naively, you might think that this domain wall can just slide around as much as it likes, but actually, because the charge density of the central bands isn't uniform, this acts as a pinning potential, and this intertwined wall can only jump in steps of 1 Moire unit cell, and this means that it's a long-lived metastable state. So now we can move on to the case where the substate actually flips as a function of position. So it's positive on the left, it's negative on the right. And so what this does is it also flips the band structure as a function of position, because when the subset flips sign, it flips the assignment of valley and Chern number of these bands. So on the left, valley k has Chern number +1, on the right, valley k has Chern number -1. And again, we can consider two possible types of domain walls. So either we have the so-called Chern wall, where the Chern number flips from one domain to the other, or we've got the so-called valley wall, where the valley flips, but the Chern number doesn't as we cross the domain wall. And both of these types of domain walls are going to be pinned by this subset step, unlike the intertwined wall, which was pinned by the underlying Moire potential. So let me just summarize these three types of domain walls that we found. First of all, I talked about the intertwined wall, where we have Chern number and valley flipping across the domain wall. Because the Chern number flips, we have these co-propagating gapless modes. On the other hand, for the sign changing subset, we have two possible solutions: the valley wall, where the valley flips but the Chern number doesn't. This leads to counter-propagating modes at the boundary. Or we have the case where the Chern number flips but the valley doesn't. Again, we have some co-propagating gapless modes. So let me just say a little bit about the method of calculation that we used here, because it's a new method that can be applied to many of these Moire systems if you want to consider the inhomogeneous setup. And so we called this the fixed Hilbert space method. So let me explain the name. So I showed you that the subset was changing as a function of position, and so we need to find a way to deal with this. And of course, you can solve the continuum model with a finite subset, but this leads to problems when you try to stitch together these different Hilbert spaces on the left and the right of the system. So instead, we use a different method. We work in the Hilbert space of the zero subset central band. So we solve the continuum model for zero subset, and then we project down the subset potential to get some effective single particle term in the Hamiltonian, which we can then give some arbitrary spatial dependence. So it could either be a constant subset, some step subset, or some smoothly changing subset. So this is a very flexible method in that sense. And the other thing I wanted to add is that we also found that a useful way to then visualize our Hartree-Fock solutions, once we've done the self-consistent Hartree-Fock, we end up with some solution, we want to visualize it. And the way we do it is by constructing the Wannier-Xi orbitals, which are wave functions that are exponentially localized in one direction, which is analogous to the Landau gauge orbitals in the standard quantum Hall effect. And so by computing the overlap of our solutions with these exponentially localized Wannier-Xi orbitals, we get some spatial resolution of our solution. So let me show you the Hartree-Fock results for one of these types of domain wall. This is the Chern wall. If you're interested in the other types of wall, then you can look it up in our paper. So the setup is here on the right. So we consider some finite system of n1 times n2 Moire unit cells with periodic boundary conditions, and we apply a spatially varying subset along the x direction. And this gives us two domain walls, one of them localized here at the center in blue, and one of them localized here at the boundary in red, and these arrows are showing these co-propagating gapless modes. And so the color coding in this figure on the left is the same as the color coding in this figure. So I've shown you the Hartree-Fock spectrum, and these blue states are localized close to one of the domain walls, the red states are localized close to the other domain wall. And so you nicely see here the two co-propagating gapless modes at the two domain walls, and from this we can, for example, extract the velocity of these modes. The other thing that's shown here is the local density of states at a given energy. So this is what you would measure in STM, for example. And so you see that these gapless modes are mainly localized close to the domain wall. You also have these bound states up here, which are localized at the domain walls. And then at some generic energy, you have a delocalized mode. And so we want to say that STM might be one method of observing these domain walls and distinguishing which type of domain wall you have in a given experiment. So let me summarize here. So we developed a Hartree-Fock scheme for treating inhomogeneous Moire systems. And we found that for magic angle twisted bilayer graphene, there were three types of relevant domain wall. There was the churn wall, where the churn number flips across domain walls. There was the valley wall, where the valley flips across domain walls, both relevant in the regime where the substrate is flipping sign, and they're pinned to these substrate flips. On the other hand, we also had the metastable intertwined wall, which was relevant for completely uniform substrates, and this one was pinned by the underlying Moire potential. So depending on whether the churn number flips or not, we have either core or counter-propagating gapless modes, and this will lead to distinct signatures in transport. For example, these co-propagating modes can short circuit the sample and then destroy the quantized anomalous Hall effect. They also presumably have different signatures in magnetization and also in STM. Thanks for your attention.
Okay, thank you very much, Glenn, for the nice talk. We have 3 minutes for questions, so the floor is open for it. So please type your questions into the chat or unmute yourself. Okay, just 1 second. Okay, so while we're still waiting for some questions, so maybe one question about the experimental observables for these churn walls and valley walls. How do you think this could be studied potentially in experiments?
So, okay, in experiments, I haven't talked much about the magnetization because we've not computed the magnetization yet. That's something that we're thinking of doing, but presumably the
so with scanning squid, probably that could be.
Yes, exactly. So this is something that I was showing these results of Andrea Young's group.
Right, exactly, right.
So they're able to observe the magnetization as a function of position. So this is exactly what we'd be interested in computing and comparing to the results.
Basically, so I think what we are all surprised about is that this is the same device where Andrea observes perfect quantization of the RXY signal. And then seeing that domain structure there, it's really surprising that you get a perfectly quantized signal in such a domain wall structure, right?
Yes, yes,
So
exactly.
it's not like one domain. If one domain would give quantized value, that would be much more obvious. That would be a much more obvious interpretation.
Yes, so then it might also come down to what type of domain wall we have here, because like I was saying, if you have these co-propagating gapless modes, these will short circuit the sample and completely destroy the quantized anomalous Hall effect.
I see. I see.
But perhaps if we have a different type of domain wall, or perhaps the short circuit isn't connecting the correct terminals, then we would still get a quantized response.
I see. I see. Okay, that's a good point. Yeah, because otherwise transport is usually not a very good probe for domain wall creation like that, unless you really assume that it short circuits it. But this whole spatial resolution techniques like scanning squid or STM are of course very good for that.
Yeah.
Okay. Do we have any more questions?
Yeah. Can you hear me?
Yeah.
Yeah. So, what kind of let's say an STM experiment do you expect? Because at the domain wall, what is the spatial extent? You would expect this to be like within 1 nanometer or less across the domain wall. Because yeah, you may get a different feature, let's say in spectroscopy. What exactly would you expect across the domain wall? That you may see a feature and it disappear across, and what is the range of that? Do you have any idea?
Okay, so first to the spatial resolution. So we find that these domain walls have a spatial width on the order of 1 Moire unit cell, so something like 14 nanometers, something like that. And so what we see is that depending on what type of domain wall you have different types of signatures. In particular, in the case of the churn wall that I was showing, you had these bound states that were localized close to the domain wall, whereas for other types of walls, these bound states don't occur because these bound states are sort of pinned by the substrate step. Whereas if you have the uniform substrate, which gives you the intertwined wall, you wouldn't end up with these bound states. So if you could observe these with STM, you would be able to distinguish what type of domain wall you have.
Okay.
Okay, any more questions? Maybe one last one. But if not, we're basically out of time. So thank you very much, Glenn. And we'll move on to the next speaker, our last speaker, who's Jose Pizarro. Jose, are you here?
Yeah, you can hear me?
Yeah, we can hear you and we can see your screen.
Okay, and can you hear also the laser at this point?
Yeah.
Okay, so hello everyone. First of all, let me thank the organizers, Lenny, Dima, and Johannes, for putting together this very nice mini colloquium, and also for giving me the opportunity of presenting my work here. So it's kind of sad that we cannot meet in person in Madrid and enjoy the good weather. Actually, I wasn't planning to show you anything, but because of this online format, I think it's good to show you a bit of a piece of the city. Actually, this photo that you can see here on the top corner is one of my favorite corners in Madrid. And it's kind of interesting. It's one side of the cathedral. And there you can see actually not a first sight, but you can see the 3 main monotheist religions at once, right? So you have the Christian cathedral, then you have this Muslim wall, which was created during the origin of the city, and also like a fountain, which is said with this Star of David from the Jewish religion, right? And as such, I'm gonna mostly talk about this Star of David in transition metallic algorithm, so I think it's perfect to put it here. And so this is part of a collaboration between myself and Tim Welling. We are both working in Bremen, all together with people working also mostly in Germany, like in Würzburg and Frankfurt, and also one person working in Chieti in Italy. And you can find whatever I'm gonna tell you now, you can also find it in this reference, which hopefully will be published soon in some journal. And also a small disclaimer, I'm not gonna talk about Moire resistance. So for me, twisting at the small angles, it's at least so far out of the table. But I want to motivate you to maybe do it in a further and future work, maybe experimentally, maybe theoretical, just to see what's happening when you take the bilayers that I'm going to show you here and rotate it for small angles and so on. Okay, so what are these Star of David systems? These are transition metal decalcogenized. I'm going to mostly speak about this tantalum diselenide, but also you can find it in tantalum disulfide and niobium diselenide. And these systems are known to develop a charge density wave state, order state. So basically, you see here in blue the transition metal atoms. So in this case, tantalum distort from their equilibrium positions into forming these Star of David. Okay, as you know, like when you change your unit cell, so in this case you enlarge your unit cell, so you basically are quenching the kinetic energy of the electrons. And then you should expect that your bands becomes flatter, right? And as the bands becomes flatter, so the kinetic energy of electrons is reduced, then correlations are more and more important. So everything in this project was motivated by this work by Michael Cromie and collaborators that was published in April 2019, so last year. And basically they were able to synthesize this tantalum diselenide into the monolayer, bilayer, and trilayer limits. And I will show you later these band structures, but I can anticipate you that actually when you go into the monolayer limit, so you have a kind of relatively large gap, which is related with the fact that the system is indeed a Mott insulator. But once you put more and more layers, the system becomes less and less correlated, right? Until for 3 or more layers, the system is a weakly correlated semimetal. And when we took a look on this, we thought, okay, well, what's happening in this middle case, right? This bilayer seems to show a small gap yet, not as large as the monolayer limit. So that means that correlations are still present, but not that important. And then because of the arrangement, so basically here in this picture, you can see the red dots and the green dots are the centers of this Star of David, right? So let me go back a little bit. So you have this Star of David is composed by this center atom, then some inner ring, and then some outer ring. So here you can see in green and red, you can see the bottom and the top layers center of the Star of David, and then they are arranged in this kind of honeycomb pattern. So altogether we thought, okay, so what can be the role of correlations here? And maybe they are related with topology in some K-Melle kind of Hubbard Hamiltonian or some Haldane Hamiltonian. So that's what we thought at the beginning to start with. And then our final goal was actually to demonstrate, while we were doing the project, was actually to demonstrate that this system is a material realization of the so-called K-Melle Hubbard model, right? And I will go to that. And material realization of these models are not so often found in nature. And actually, I don't know if there's any other kind of material realization of these models. So if you know, you can tell it. Okay, so for that and I don't know if I will have time because I think we will miss like 2 minutes that I will otherwise just use to explain this 180 degrees rotated. But I will mostly focus about this non-twisted case, in which we basically consider the Star of David's arrangement is like you can see here in this top right panel. So you see the bottom in blue, the bottom layer in blue, the top layer in red, and they are arranged in this kind of honeycomb lattice pattern. So basically, even though the system looks complicated because you have like 13 atoms per Star of David times 2, because you have a p layer, you have 26 atoms in your unit cell. It's kind of rather simple because at least the low energy band structure is going to be kind of rather simple because it's going to be controlled by the center of the Star of David, basically. And so this is actually what happened for the band structure. On the left, you see the monolayer case. On the right, you see the bilayer in this honeycomb arrangement. And as I anticipated, because of this enlargement of the unit cell, then you find that you have a very flat band at the Fermi level in the monolayer. So I think the bandwidth, if I remember correctly, is around 20 milli-electron volts, something like that. But then when you put the second layer on top in this honeycomb arrangement, then the system becomes more dispersive. And that's a signature, and it's in line with what Michael Cromie and collaborators found, that when you have when you put another layer, then you are increasing the bandwidth, or equivalently you are increasing the kinetic energy of the electrons, and then your system becomes less correlated, right? And this is signaling also to the point that here what is making or playing all the music in this material is actually the interlayer coupling. I think this is slightly different from magic angle two-step bilayer graphene. In magic angle two-step bilayer graphene, you have the opposite relationship, right? You have the intralayer hopping is what is dominating over the interlayer one, right? But even if the system is, like I said, it looks complicated at first sight, it's a simple bilayer so two bilayers put on top of each other with this Star of David. So it's kind of seems complicated, but everything is just controlled by the center of the Star of David. And like they are arranged in this honeycomb pattern, actually the band structure is rather simple. If you think about this, so focus on this red line, right? So if you see it, it's just simple. If you can write down a honeycomb, a tie binding model for a honeycomb lattice with first, maybe second or third nearest neighbor, then you will reproduce very well this band structure. And actually, like we wanted to see what's happening with correlations, but also with topology, we also include the spin-orbit coupling here. And also the effect of spin-orbit coupling can be easily reproduced by a small opening, a gap opening at the K point, right? So generally, when you want to include this spin-orbit coupling, then you should include this, at least in this K-Mele and Haldane model, you should include these imaginary hoppings here with some special phases. But I think for this audience, it's simpler to just show the continuum model for this material, and it's just a Fermi velocity, like you will find in graphene, but here is renormalized because your bandwidth is renormalized, right? Then some RASVA, some alpha R2, some RASVA term that in principle can be neglected. But what is important is this lambda SOC, which is actually the so-called K-Mele spin-orbit coupling term, right? It's basically that when you include the spin-orbit coupling term at the K point, instead of finding a Dirac point, you will find a gap, which is twice the value of this value, right? So then with all of this, we just went into study topology, and I will go a bit quick here, basically because this is already well known. We consider this bilayer being in a kind of an external perpendicular field. An external perpendicular field can be translated into a staggered potential, or the name of this staggered potential is Semenov mass, right? So this delta M here. So for a small, or for zero, or for a small field, so the system is gap. Then at some critical, a critical field, then the gap is closed, and then you find again Dirac points, and then for larger fields, the gap opens again. And the difference between these two insulating states or semiconducting states are that the one on the left is topologically non-trivial, or also called quantum spin Hall state, and the one on the right is topologically trivial, right? And this is related with this onion phase diagram, in which you have in the x-axis the electric field, and in the y-axis some RASVA coupling. Then we also study what's going on with correlations. And basically we did in two approximations. One is dynamic and field theory. This is used to treat what's happening locally for the correlations of electrons. So basically it tells you how electrons correlate between each other when they meet in the same atomic position. While this TPSC is this two particle self-consistency, just tells you also what's happening non-locally. So what's happening when electrons correlate when they are in different atomic positions. But in both cases, for the quasi-particle weight, which is a measure of how strong the correlations are, they give similar results. So then you can argue against me, like if this is a strongly or not correlated system. I will say that it's in the intermediate correlated regime, because if you want to be a correlated system, you need like a smaller number. So these numbers will be, instead of 0.75, will be like between 0.4, 0.1, right? But still correlations are important, because if you go to the non-local TPSC, then we found that the system develops these antiferromagnetic correlations below 40 Kelvin, right? And so altogether, all that I told you, those studying this K-Mele plus Hubbard model can be summarized in this very nice phase diagram. So here on the y-axis, you have the electric field. On the x-axis, you have the interaction, the local interaction, and you can find the 3 different phases that are relevant for this honeycomb Star of David charge-sensitive system. So I told you about this topologically non-trivial, so this quantum spin Hall insulator, the trivial one. So one can tune from one to another by changing the electric field. Then this antiferromagnetic insulator is what results from non-local correlations, right? And then actually our claim is that this system resides in a region in which you can, I think the most interesting region, which is where all the 3 phases can be accessed by just changing an electric field. So you can move from this antiferromagnetic correlated insulator to a quantum spin Hall phase to a trivial one insulator. So as I find that very cool. And also that you can move in the X direction, but just instead of taking this tantalum, this selenide, you can also take one of these other Star of David systems, or also by changing the external screen, you can move towards the left of the diagram, right? Very easily. Now the motivation for you, so far I just talked about flat bands, but no Moires. So now my motivation for you, also like I said, experimentalists and theorists, is try to see what's happening with this kind of phase diagram once you put like a small angle, right? Maybe more phases will appear because the system is already correlated before entering into this twist angle. So maybe you can start to find some Mott insulator in the region which comes here. I cannot tell you because it's just a speculation. It just deserves his own probabilization. And I don't know how I'm time. I think I have. How I'm time, Tima? Do you know? It's like I have like. You
have 5 minutes.
5 minutes left. Okay.
Yeah.
So, well, but we quickly, I will talk about this 180 degrees. So basically, we wanted also to check what's happening when you break the inversion symmetry of the system to see what about topology, correlations, and so on. But basically, when you break this inversion symmetry, you have the previous K-Melle Hamiltonian, so this Fermi velocity plus lambda shock, right? Plus some other extra spin-orbit coupling terms that emerge naturally in this 180 degrees twisted bilayer. The most important here is maybe these 2 ones. So now you have there is an intrinsic staggered potential. So already the system is gapped not only by the lambda shock, but also by this intrinsic term. But also this B10, which now I don't remember very well, it's something about Bali-Seaman coupling or something like that. That is kind of tricky because this term, this B actually kills the kind of quantum spin Hall state that you find otherwise in a K-Melle term, right? So there is no topological invariant in this material. Still, the material is itself interesting because it shows like at some critical field, the system shows a closing gap with a quadratic behavior. Also, this kind of camel toe thing also close at some point might be interesting for some instabilities physics and so on. But we didn't check anything else apart from, so correlations were basically the same as in the non-twisted case. But then we stopped the project here. And yeah, that's everything I wanted to tell you. And I'm open to questions that you might have. And with that, I think I was
okay. Thanks a lot, Jose. Just before I move on to questions, I just wanted to tell everybody that we ask you to stay 1 minute longer, so we can make a conference picture with everybody. So please, right after the question session ends, please just stay a little bit with us. Okay. So do we have any more questions for Jose? So, okay, so please either type or please just unmute yourself and speak freely. Okay. And so I have a question about the first part of your talk. Mm-hmm. So you didn't consider any screening effects there, right?
Do you mean external?
Because I know you had previous work on screening as well, right?
No, we didn't consider any. So yeah, we didn't consider any dielectric engineering screening. If you mean that,
right,
we just
exactly,
simply took the internal screening and then calculate these.
Oh, okay.
Over there. But then the point is like exactly what you said. It's very important. It's like, okay, that U just locates the system here, but then you can tune towards the left if you put some external screen. Right?
So Lenny is asking, do you expect to change the material if you to reach more strongly correlated systems with smaller quasi-particle weight?
Good question, because for me it's not clear that actually the Hubbard U between different and the bandwidth between different systems is not slightly different. So in niobium the selenide is slightly less correlated, or the U is smaller, and in tantalum disulfide is slightly more correlated because both the U is a bit larger and the bandwidth is smaller. But yeah, this is kind of tricky. Maybe a way of changing the quasi-particle weight is actually going into a small rotation angle and actually looking for even flatter bands than these ones, right?
Okay, so thanks very much, Jose. So probably we'll just thank you for your nice presentation, and I also just want to make some final remarks. So first and foremost, I want to thank the conference organizers, so the organizers of the entire EPS conference, which are Maria Jose Calderon, Herman Sudarov, and Jose De Terrasa. And in particularly Maria Jose, who was the Zoom host for all these days and who really made the organization of this possible. And for the mini-colloquium, most credit goes to Lenny Bascones, who really did all the heavy lifting in organizing this, mini-colloquium. So thanks a lot. Special thanks to Lenny, and of course also special thanks to Johannes, who also helped organizing this. So with this, I would like to ask everybody to open up their videos. So we would be great if we can see all the faces on the screen. And then I guess we can all smile a little bit. So who's taking the picture? I don't know.
Jose is taking the picture.
Jose's taking the picture.
Yeah, I can take a picture. So yeah, I wait a second for all of you to, yeah. Okay, so 1, 2, 3. Great, thanks.
All right. Okay, thank you so much.
Thank you.
Bye-bye.
Yeah, you can unmute yourselves if you want to talk.
Ok, muy bien.
Sí, no he podido estar en nada, o sea, he estado haciendo otras cosas. Así que ya yo...
No te preocupes.